I want to start out very early on in this course by having a look at a few figures, just so that we can contextualize how important web app security really is. And I thought this was a really good place to start. So this is from White Hat Security's Statistics Report of 2015. And the big figure here is obviously this 86%. And that's the proportion of web apps that they've found to have at least one serious security vulnerability. And most of the time it's far more than one. So with that prevalence of risks in applications, is it any wonder that we are seeing so many breaches? The bottom line with this figure is that if you look at any web application on the net today, there's a very high likelihood that it's going to have multiple serious security risks. So that is a very high, very alarming figure. But there is an even larger figure that I want to touch on now as well. And it's this one. Almost every single vulnerability that gets exploited is already known. There's already a CVE for it, a Common Vulnerabilities and Exposures record. So that is, it is publicly documented that these risks exist and need to be patched and defended against. These should not come as a surprise. So this number, which is so close to 100% in Verizon's 2015 Data Breach Investigations report, is showing that software keeps getting exploited via known risks, things that we just simply shouldn't see exploited. Because the risk is publicly documented. This is not news to anybody, yet here's this figure, almost 100%. But a question that's always raised is that once an exploit happens, what does it actually cost? That's always a hard thing to tie down into a tangible number. But let me give you one from a very significant event in 2015. It's this figure. That's $500 million. And not only is it $500 million, but that's one event, and it is 1 week after the Ashley Madison breach occurred. 1 week is all it took to have $500 million worth of class action lawsuits already mounting up against Ashley Madison. Over time, this number will become significantly larger, and it doesn't include all the legal costs that Ashley Madison will go through. It doesn't include the loss of revenue due to reputation impact. And it certainly doesn't include the significant costs they've incurred to try and secure the system once the breach actually happened. That would have run into many millions of dollars very, very quickly for an incident of this scale. So whilst it's always hard to try and put a figure across the entire industry, being able to pick one event like this and show just how significant that cost can be within such a short time frame after the incident itself goes some way to putting the value of security in context. So that gives just a little bit of a sense of where we're at with web security at the moment, both the propensity of risks, how well known they already are, and what sort of costs you can be looking at when things go wrong. Let's now move on and start actually taking a look at how attacks against web applications really work. I want to begin by taking a very high-level look at web application security. And I'm going to start here. Let's imagine these three components in a web application. Now, often you'll very loosely hear this referred to as a 3-tier architecture. So having a presentation tier, so this is what will render into the browser. Having a logic tier, so this is where a lot of the processing is done on the actual web server. And then having a data tier, so very often a relational database management system, which obviously manages the data in the system. Now, along with the various technology components of the system, clearly we also have a user. And the point of interaction for the user is via their browser. That's probably pretty obvious, but we'll see how that fits into the broader picture of application security in just a moment. Let's now bring our attacker into the picture and talk about some of the risks which they're looking to exploit. Now, clearly, one of the first points the attacker is going to look at is the presentation layer of the app. They're going to open it up in the browser, have a poke around and see what they can find. Within that presentation tier, they can easily identify numerous risks which may then lead to them exploiting the system. We'll have a look at how the attacker begins by exploiting things in the browser when we get to the module on attacks involving the client. But at this level, we're typically talking about things like cross-site scripting, cross-site request forgery, and exploiting weaknesses in the transport layer security. So all of these do tend to touch on the client. We're also going to talk a lot about going direct to the web server, circumventing the client altogether. Because when the attacker starts talking direct to the web server, outside the scope of the browser, outside the HTML that it renders, we're now starting to talk about attacks like SQL injection, lack of proper access controls. So the attacker just discarding the browser altogether, going straight to the server and exploiting weaknesses in the app. Now, one thing that will often be present in a web application ecosystem is a firewall between the logic layer and the data layer. So what we're trying to prevent here is the attacker going straight through to the database. Because what if the attacker can identify the machine that that database is running on? Might they be able to connect directly to it? So for example, might they be able to brute force the logon to the database? Or might they be able to exploit a risk in the database software? So this is why we typically try and isolate that segment of the infrastructure. Now that doesn't mean that the attacker still can't get to the data using a risk like SQL injection. And we'll talk a bit more about SQL injection in this course as well. So whilst things like firewalls do help in certain cases, as we progress through this course, you'll also see how attackers are very adept at actually circumventing security controls as well. Now, one other thing that the attacker does try to exploit is the user themselves. So how does this happen? How does an attacker exploit a user? Well, this is where we get into things like social engineering. So can the attacker trick the user into clicking a link in a phishing email? Now that might be all it takes to mount something like a cross-site scripting attack. So this is actually an attack against the user via phishing, which then results in an attack against the presentation layer by tricking the user's browser into making an unintended request, which might then give the attacker something like an authentication cookie, which they can then use to mount attacks against the logic layer, against the web server. So these attacks often chain together. One thing leads to another, leads to another. And as we go through this course, we're going to be talking a lot about defense in depth. So how do we make sure that there are multiple layers of defense such that if one or perhaps even two go wrong, it doesn't allow the attacker to exploit the system? Now, there's just one more thing I want to show you in this diagram, and it's this. Attacks against web applications are not necessarily constrained to the web app itself, particularly when these applications start to sit in the same network segments as other infrastructure. So for example, if the attacker can get a shell on the web server, so actually have full remote control over that environment, what else could they then connect to? What environments could they pivot between or gain access to? It opens up a whole other can of worms. So whilst we're talking about web applications and exploiting risks in web apps in this course, just keep in mind that this can also be a gateway to much larger things than just web apps alone. So that's a very high-level view of web app security. I want to go on now and start looking at some of the specific paradigms that you may be familiar with if you're building web apps, but we're going to look at them from the attacker's perspective now, and we're going to talk about how they might exploit these things. Let's go and look at those now. I want to talk about query strings, routing, and HTTP verbs, because we're going to use all of these things in the course as we progress. And more specifically, we're going to exploit them in order to hack web applications. So it's important that we go through and just recap on precisely what these three constructs do. So let's start here. And we're going to start with a fictitious URL, just like this one here. Now, one thing that's really important to remember when we look at the construction of a web application is that there are conventions so patterns that are typically followed, as well as very discrete implementations within web apps which may well actually be anti-patterns, so may not comply to accepted wisdom and accepted conventions. I'm going to talk mostly about conventions and how these patterns are normally used. So for example, query strings. Now when we look at this URL, we can break this down into logical components. So for example, there's a scheme. It's HTTP, it's not HTTPS. Obviously there's a domain name, website.com. But what's important in the context here is that we have a resource type, and that is widgets. So logically, and again via convention, what we're seeing here is that there is this concept in the system of widgets, and this resource is referring to widgets. In fact, it's very specifically referring to widget number 27. So the query string is very specifically telling us which record we should be seeing. So you'd see a resource like that with widget 27 on the page. You'd change the ID to widget 28, and logically you would get a different widget. The relevance to security is going to come when we start looking at what we can change that ID to, such that the web application might do something that it wasn't intended to do. Let's take another query string example. So we'll take a URL like this. Now this query string does something fundamentally different, in that what we're looking at now is an action. So query strings can be used in multiple different ways. It might refer specifically to one entity within the data layer, or it might give the application an instruction on what it should do. So semantically, so that is what would make sense just by the way it's written, if I went to this URL, I would expect to see a list of widgets and they would be ordered by the name of the widget. Now this is all probably pretty self-explanatory, but it's important context because as we progress through the course, we're going to start to look at how we can modify these query strings in order to get this app to behave differently. So this context about sometimes referring to resources, other times referring to actions, and indeed not being limited to either of those, you can make up whatever query string you like that does whatever you like. But typically these are the patterns and conventions that we see. Let's move on and take a look at another pattern. Let's look at routing. Routing has become increasingly popular as a replacement for query strings. So a route would look something like this. And a route like this would functionally do the same thing as the first query string on the previous slide. It would get widget number 27. So it's really a way of describing the resource in a cleaner fashion than putting a query string on a URL. We still have the resource type, which is widgets, and we still have that resource ID, but now it's all part of just one nice URL. The point from a security perspective is that we could still modify this, and specifically we could still modify that resource ID and get a different resource out of the system. Now to extend the paradigm from the previous slide, where first we looked at a resource and then we looked at an action, this is the sort of URL that we'd see in a routing implementation. Now here's our action, and that's pretty self-explanatory. And the relevance here is twofold. Number one, a route can describe an action. And clearly if you hit this URL, what it's implying is that it would attempt to delete widget 27. Now what's interesting from a security perspective is if it would actually do that if you didn't have appropriate authorization. But number two, the other thing that's interesting about that is as we start to see these conventions, even if you didn't see a URL that had a delete in it, you may start to wonder what would happen if you put a delete in it. So if you saw that top URL and you said, hey, this looks like a route, this looks like the app is using a routing convention, I wonder if that would extend to applying an action like a delete. We're going to talk more about that as we get into untrusted data a little bit later on in this course. There's one other pattern I want to look at first though, and that's HTTP verbs. Now this is a very semantic way of constructing requests. So here's what I mean by that. Let's take this one. So this is pretty much what we just saw on the previous slide. All I've done is listed the HTTP verb there as well. So it's a GET request. And of course, that's the default. If you just put a URL into the browser, it will make a GET request. Inevitably, in this case, we're going to get widget number 27. What if we changed it though? So what if we changed the verb from a GET to a POST? Well, a POST is typically used to create a resource. So with a request like this, you'd expect to see a request body that had a widget in it. And in fact, you'll see this URL doesn't actually specify an ID. So what would probably happen in this scenario is you'd have other properties of the widget entity, perhaps a name or a price or whatever it was that the system stored about the widget, and then the system would create that widget and assign it an ID. That'd be a pretty typical pattern. So very similar URL, just a different HTTP verb that gives it a different semantic meaning. But what about one like this? So this is a put request, and put is an entirely different HTTP verb, which normally implies that you're wanting to update a record. And in fact, you can see the URL has still got number 27 in it. So in theory, someone hitting this URL is attempting to actually change widget number 27. Now the question an attacker might ask in a system which is using a very semantic HTTP verb implementation is if they saw that first URL, the GET URL, might they possibly be able to change a GET to a PUT and actually overwrite it? Or what about this one? What if they changed a GET to a DELETE? DELETE is a perfectly valid HTTP verb. And in an implementation that does make good semantic use of HTTP verbs, this would possibly delete that resource. Now it all comes down to how the system is actually implemented. You particularly see HTTP verbs used in this way in very RESTful applications. So that is representational state transfer, which is what we normally see implemented in APIs. So in this modern era where we have a lot of single page apps with a lot of asynchronous client-side callbacks, and likewise we have a lot of mobile clients and IoT clients talking to APIs, using a REST-based pattern that implements HTTP verbs in this way is very common. So it's something to think about when you see this sort of pattern. What might happen if you change that verb? We'll talk more about verb tampering as we get into the module on tampering of untrusted data. Now that we've covered some of these typical web app behaviors, I want to go and look at a real web app and show you how we can start to find security constructs in the publicly facing source code. Let's go and take a look at that now. This website is hackyourselffirst.troyhunt.com, and it's a website that I use extensively throughout my Pluralsight courses in order to demonstrate security vulnerabilities. Now what I want to talk about very briefly here is how we can discover security constructs just by looking at what's been returned to the client, and in this case looking at what's in the browser. So here's what I want to do. Let's jump over to the register page. And one of the things we can obviously do is view the source code. The Control-U shortcut will take you there. Now by viewing the source code, we can see exactly how this page is constructed. Now what can we tell from that? Well, let me give you an example. I'm going to scroll down a little bit. And here on line 51, we can see a form. So this is where the register form posts to. So one of the things we can see immediately is where our data is going to go. Now because there's a form there, it's also very easy to see all of the form inputs. In fact, let's do this. I'm just going to do a Control F and I'm going to search for input tags. So the first one that's found here looks to be the search input. Let's jump down to the next one. And this one looks like it's for the email address. The next one is the first name. Then the last name. Now here's the one for the password. And we can clearly see some of the security controls around the password based on the attributes of this tag. So we can see a data validation for the max length. It can be no longer than 10 characters. And we can also see a required regular expression pattern. So this looks like just alphanumeric lowercase or uppercase only, which is quite a restrictive password requirement. Now, none of this is too sensational. The point is that you can discover a huge amount about the security profile of a web application just by looking at the information that's already returned to the browser. So the discoverability of those client-side security constructs is very high. Let's look at one more thing. I'm going to go and close this tab, and let's go over to the search box, and I would like to search for Ferrari. Now we've found one result here. If I view the source code, so Control U again, and then I jump down to the end of this source code, we can see a bunch of JavaScript here. And this first block of JavaScript is telling us a couple of things about how the page actually behaves. And the point here is that this is actually functional. So in this case, it's setting a behavior on the rows that are returned in the results, and it's also populating the search term box. So that was the one we saw up in the navigation bar of the site. Now again, none of this is too sensational. Most technology professionals are aware that you can view the source code of the page. The point I want to reiterate though, is that the attacker can also view this. Not just this, but all the JavaScript files, all the data annotations on HTML tags. All of this actually discloses a lot about the way the application is put together. And it's often as simple as just viewing source. So there is a huge amount that we disclose about the structure of our web applications just by virtue of the fact that this information has to be returned to the browser. Now speaking of browsers, let's move on and take a look at some of the protections that they offer their end users. I want to talk about the way browsers can protect users and what that means for the attacker, or for the ethical hacker as it may be, in terms of their ability to exploit systems. Now, browsers have evolved enormously in recent years, and there's a bunch of different things they can do now to help protect users above and beyond the defenses in the application itself. So here's a good example: protection from phishing sites. Browser vendors have very extensive lists of malicious sites. And what that means is that if a user attempts to go to a site that has been classified as a phishing site, they might see a warning like this. Chrome is not very subtle when it thinks something is wrong. And this is a great example. This site is legitimately classified as a phishing site. If a user goes to this site in Chrome, there is no possible way they won't realize that something could be wrong. Now, this is a great way of defending users. And if we think back to the earlier diagram, the one with the three-tiered architecture and the user, one of the attack vectors was the attacker actually trying to get the user to follow a link to a phishing site. This stops that. Let's go and have a look at some other defenses. Another thing that browsers do a very good job of is protecting against invalid SSL certificates. So what happens if there's a man in the middle trying to intercept a user's traffic and putting their own certificate in the midst of that communication? We're going to talk more about SSL, or more correctly, what we now know as TLS, when we get into the module on attacks involving the client. But just for context, whilst we're talking about protections offered by the browser, here's what happens when that certificate is invalid. Once again, Chrome is not real subtle. It's very, very clear that there is something wrong here. Now, with both this case and the one just before on phishing attacks, you can still go through and click through this warning if you like, and you can proceed unsafely, as they say here, but you can't do it by accident. It's a very, very conscious decision. Now let's have a look at what's going on here as well, because it's not that there's necessarily anything wrong with Ferrari.com. It's just simply that they're not serving a valid certificate. So they're not actually implementing HTTPS on that domain. We can see that if we go up and click on the padlock and we have a look at the certificate information of the site, we can see that the certificate being returned is actually a wildcard. It's for star.cloudfront.net, which is inevitably their hosting provider, serving up another certificate not valid for this domain. The point here, though, is that the browser protects the user, and particularly for sites that are intended to be served over HTTPS, if the browser doesn't get a valid certificate that it recognizes, it will keep the user away from the site. It will jump in before anything sensitive is sent over that connection, which could then put the user at risk. Let's go have a look at some other protections. Another protection that Chrome in particular is getting very good at lately is flagging when there's weak cryptography used. So we're talking about deficiencies in the SSL or TLS implementation. So ultimately in the security of the HTTPS communication. And in fact, whilst I mention HTTPS, we also get very good warnings these days about mixed content. So this is when we have a page that's served securely over an HTTPS connection, but then it has content on the page served over HTTP. In fact, let me give you an example of both these two, weak cryptography and mixed content, because I've got a site for you that demonstrates both these at once. So here's a good example of those two things, both the weak cryptography and the mixed content. And we can see here Chrome is giving us a yellow triangle on the padlock. And if we go and take a look at why that is, it tells us your connection is encrypted using an obsolete cipher suite. So yes, there is HTTPS, but it is a weak implementation. Further, this page includes other resources which are not secure. And the point I'm making here is that Chrome has identified both these risks and given us a visual warning. So I can't use this site now without seeing warnings from my browser saying that it's not really secure enough for a couple of different reasons. So that's just one more example of the browser getting very good at protecting users. Let's go and look at a couple of others. Another defense that browsers have gotten quite good at recently is reflected cross-site scripting. Let me show you the behavior in the browser, and then later on in the module on attacks involving the client, we'll look at the actual execution of an attack. I'm back on the Supercar Shodan site, but you may notice one tiny little difference. The URL is prefixed with local. So this is one that's just running on my machine. You can't see the behavior that I'm about to show you on the publicly facing website. But I've set my local one up to demonstrate a very specific behavior. I'm going to paste in a URL, and this URL has a cross-site scripting attack in it. I'm going to load this URL, and the page looks kind of normal. There's not a lot going on here, but here's what I wanted to show you. If I hit F12 to open up the developer tools, we can see a great big red warning. The XSS auditor refused to execute a script. Now what's actually happened here is that Chrome has seen a request for a URL that has some potentially malicious script in it, which has then been reflected in the response. We'll talk more about why that's significant later on, but the important thing here is that the warning tells you that this has actually been blocked. So even though the web application itself has a cross-site scripting vulnerability, the browser has stopped it from running. Let me show you another implementation of that. This is Internet Explorer 11. Let's do the same thing. See the warning down the bottom. Internet Explorer has modified this page to help prevent cross-site scripting. A little bit more overt than in Chrome this time. But this is the point. The browsers, even different flavors of the browser, are getting much better at defending the users. Let's go back and touch on just one more point. The last one I'll touch on here is security headers. I've got another Pluralsight course on Introduction to Browser Security Headers, and I'm talking about things like HTTP Strict Transport Security, or HSTS, HTTP Public Key Pinning, HPKP, and Content Security Policy, also known as CSP. All of these are headers that can be returned from the website that then instruct the browser how to secure the website. So browsers have gotten intelligent enough that they can block things like cross-site scripting or cross-site request forgery based on the headers returned from the website. So browsers are getting very, very intelligent, particularly the newer iterations of browsers. So all of these are a good step in the right direction. Of course, none of this negates the need to properly secure the web app. This is another one of those layers of defense that I mentioned earlier on. But now that we've covered this, let's go and take a look at what it is that the browser can't defend against. As we just saw, there's a lot that modern browsers can do to help protect users. But there's also a lot that they simply can't do. So for example, a browser cannot protect an application from parameter tampering. There's nothing to stop an attacker from just modifying attributes of the request. So earlier on, we looked at the query string and how a query string might describe the resource that should be loaded from the system in the request. There's nothing to stop the attacker from just going and modifying what the ID of that resource is. The browser doesn't know that it's going to be a malicious attack. And indeed, the browser doesn't even need to be there. The attacker can issue HTTP requests directly to the server via all sorts of other means, and we'll have a look at some of those throughout this course. Browsers also can't protect against persistent cross-site scripting. Certainly it can't do it reliably at the moment. So persistent cross-site scripting is when there's already an attack in the database, and you can make a very normal request to a resource on a website, and the attack is simply loaded up and appears in the response. That's very hard to protect against because the browser really doesn't know what is malicious and what is not. And of course, we can't change the fact that attackers can just make direct HTTP requests. I just touched on that with parameter tampering. They can also use it to try and access resources that they're not authorized to. They can also make direct HTTP requests to do things like exploit a SQL injection risk. And really, the browser isn't meant to defend against these things. The browser defenses that we just looked at in the last clip are predominantly there to protect the person using the browser. They're not there to stop someone from maliciously attacking the website. So being clear about where these boundaries are, what the browser can protect against, and indeed what it's there to protect against in the first place, versus what it can't, is important to understand. Now there's just one more thing I want to look at before we wrap up this module, and that's what I'm not going to talk about in this course. I want to cover two really important things here simply because their omission in a course about web application security would be really obvious. The first is SQL injection. And the reason I'm not including SQL injection in this ethical hacking course is because I've already got an ethical hacking course that talks about nothing but SQL injection. Later on, I'll mention where SQL injection would logically fit in the Hacking Web Applications course. And then if you really want to get into SQL injection, go and watch Ethical Hacking SQL Injection. The other one is session hijacking. And it's the same story. I've got a dedicated course as part of the Ethical Hacking series on session hijacking. And again, when I get to the right point in this course, I'll remind you that if you want to go and brush up on your session hijacking skills, go and watch that dedicated course, Ethical Hacking Session Hijacking. So again, for both of these, I'll point out where they logically fit into this course, but I'm not going to cover them in detail here because they've been done so exhaustively in those other two courses. So that's it for understanding security in web applications. Let's go and take a look at the summary. Let's summarize the module. And the first thing I made really clear is that hacking web apps is really big business. Almost every web application has at least one serious security vulnerability. And as good as every single vulnerability that was found in these web apps is already known, that Verizon figure, 99.9%. When it comes to the impact of actually hacking them, seeing a web application like Ashley Madison see $500 million of lawsuits within only 1 week of being hacked is a good indication of just how serious an incident can be. One of the very next things we looked at was the different attack vectors in web apps. So seeing attacks not only against the presentation, logic, and data tier, but also against the user should give you a good indication of just how many ways web applications can be exploited. We're going to look at all of those as we go through this course. In order to get you ready for that, we also looked at understanding the web app structure. So query strings, routes, HTTP verbs, these are the fundamental building blocks of modern web applications, and understanding how they work is going to help you be more efficient as an ethical hacker. And lastly, browsers are getting very good at implementing defenses, but there's only so much they can do. It's fantastic that they can identify a phishing site or block a reflected cross-site scripting attack, but they can't defend against all sorts of different attacks that attackers themselves will mount against the web application. And indeed, in many cases, the attacker will just take the browser entirely out of the picture. And in fact, that's one of the very first things we're going to do as we get into the next module on reconnaissance and footprinting. So let's go and jump into that right now. The first demo I want to look at in this module is spidering. And spidering is the concept of crawling through a website, following all the links that exist in that site and creating a map of how it functions. So think about a spider web. And indeed, that's often an analogy for the internet itself. But think about it in the context of an individual website, where you start at one point and then there's a link to somewhere else, then to somewhere else and to somewhere else again. And when we talk about spidering, we're talking about crawling all of those links and building up a picture of how the site is put together. Now, this is one of the most fundamental principles in reconnaissance and footprinting, because it's really just following links on the site. It's not necessarily doing anything malicious. And certainly there are a lot of tools that can spider a site, so crawl through it and then create a visual map of it. The tool that I've chosen to demo this is NetSparker. Now, I've used NetSparker before in a number of my other courses because I find it's a really easy to use dynamic analysis tool. So that is, you point it at a URL and you let it go. It doesn't just spider the site, it does a bunch of other things as well. But I'm just going to focus on the spidering component of it here. So let's do this. On the screen at the moment, you'll see the Start a New Scan dialog. And in the target website URL, you can see the hackyourselffirst.troyhunt.com address. Now, all I'm going to do is click on Start Scan. And now it is spidering. And we know it's spidering because down in the bottom left-hand corner in the dashboard panel, we can see it crawling. Now, even though this is quite a small site, the scan is going to take quite a while, because what NetSparker is going to do is not just follow all the links that are actually explicitly referenced on the site, but also check a few other common ones as well. And you'll see what I mean by that when we have a look at the results. NetSparker also does a whole bunch of dynamic analysis. So that is, it actually tests for security vulnerabilities as it scans. Because it is going to take a while, we're going to let it run and then come back to this shortly. Okay, so NetSparker has now run. The whole process is complete. We've got a bunch of results here on the screen. We can see a nice set of traffic light color coding about critical and medium and all sorts of other ratings for vulnerabilities that's found on the site. What I want to focus on though is the sitemap off to the left of the screen. And this is really where the spidering has happened. So as we scroll down through this panel, what you'll see is literally a map of the site. We can see all the folders that are there in the site. We can also see things like the robots.txt. So this is the file that normally tells search engines what they can, and most importantly, cannot access and then index on the site. Now, robots files can be especially interesting So let's go and have a look at this one just here. Now over to the right of the screen, we can see a number of panels. The one at the top is the request panel. The one just below that is the response panel. And I'm particularly interested in what's come back in the response from that file. And in fact, if we scroll down a little bit, we can see the response headers, and then we can see the contents of the file. And these disallowed directives are particularly interesting. The disallowed directive on line 17 is really interesting because that's telling us that there is a path on this website called secret admin. Now that to me, with my attacker hat on, does sound rather attractive. Now because the robots.txt describes these resources on the site, NetSparker will crawl them. So what that means is if we now scroll back down through our sitemap, we will find the path called secret admin. So indeed, NetSparker has picked this up from the robots.txt and it's gone and crawled it. Now I'm particularly interested in the response, and I'll give us a little bit more room down here so we can see it all. Now as before, we can see all the response headers, and then as we start to scroll down, what we're going to see here is an HTML document. And in fact, we can see the title here says access denied. If I keep scrolling down though, as I get down towards the bottom of the page, we can see something particularly interesting on line 74. Download the database backup. Now this is obviously really useful information. I, as an attacker, would actually be rather interested in getting my hands on the database backup. And this is the sort of information that's very easy to discover by spidering the site. Now obviously this is a pretty basic example, and I've jumped straight to the really interesting parts of this. But there are many times that you'll look at a website and then look at the robots.txt and find it points to something particularly interesting, often somewhere that is not properly secured, that's been added to that file in order to keep it out of search engines, but then hasn't been properly secured because there's been the expectation that no one will find it because it won't be searchable. So that is a very simple example of what spidering does and what some of the information is you can discover by crawling through the website and picking up all of these different resources, some of which can be particularly interesting. The next thing I'd like to look at is forced browsing. And when we talk about forced browsing, we're talking about a similar concept to what we just saw with spidering, but instead of just following through known paths in the application, we're going to go and hit a whole bunch of stuff that may not even exist. Now the reason we're going to do this is because we want to try and discover other resources which may not be accessible just by either following the links that are visible on the site or accessing common resources like the robots.txt file we just saw. So for example, might there be an admin directory? And for that matter, could there be an unprotected admin interface behind it? Or perhaps an admin interface that we could then probe further to see if it had vulnerabilities in it. Perhaps there's a SQL injection vulnerability, which would get us as an attacker into the system. So as part of reconnaissance and footprinting, forced browsing helps us build up the profile of how the application is put together. Now in this demo, I'm going to use Burp Suite. I'm going to use the free edition, and we will see some limitations on that in just a moment, but it is going to be enough to demonstrate the concept. And again, just like with NetSparker, there are other tools that can do forced browsing. I've just picked Burp because it's very easy to demonstrate. So here's what I'm going to do. I'm presently proxying my machine through Burp. So I've gone into my proxy settings and I've pointed them to the default setup that Burp gives us, which is running on 127.0.0.1 and port 8080. Now here's what that means. I'm going to go and bring up a Chrome window. So here's our Supercar Showdown website, the vulnerable site, and all I'm going to do is click a link. So we'll just go up here and click on the leaderboard link. Now in the background, in Burp, you can see that the proxy tab just went orange. So let's now jump back to there and click on that tab. Now we'll see as we click on proxy, beneath that we can see that there's a bunch of other tabs, and the intercept one is both selected and orange. And what we're now seeing here in the raw tab is the request that we just made in the browser. So it was a GET request to /supercar/leaderboard. So what's happened here is that Burp has just captured that request. What I'm going to do now is go down to this raw request and right click. This is going to give me a bunch of options, but the one that I want is send to intruder. Now once we do that, the intruder tab goes orange. Let's now go up to that and we can see a few more options here. A little bit further down the screen we have this target, and the attack target is hackyourselffirst.troyhunt.com, so our vulnerable website. What I want to do now though is jump on over to positions, and when we load this tab we can see the raw request here. Now not only do we see the raw request, but we see some highlighting, and it's here on the cookies, session ID, visit start, so on and so forth. What Burp allows you to do here is define dynamic components of the request. And in doing that, you can then go and launch a whole range of different attacks that substitute those dynamic components with other values. In fact, in my course on ethical hacking SQL injection, I show how to do fuzz testing using Burp and substituting these highlighted sections here for a whole range of different typical attack scenarios. In this case though, what I want to do is just clear those out. And I'm going to go over and select everything in the path after the /. Now I'm going to add that. And we can see that this section now gets highlighted. So this is going to become the dynamic component that we're going to do our forced browsing with. So really what we're saying is we are going to now substitute the URL for other values and then see what comes up. Now that we've defined that area, let's go and pick a payload because we need to decide what we're going to substitute into that path. Now what I'm going to do is load a list of directories that I would like to force browse. Now before I do that, I want to show you what a typical one looks like. So let's have a look at this one. Here's a good example, and this is the one that's used in OWASP's ZAP project. And as you can see here, after we get past the initial comments, we're seeing paths like CGI bin. So that would be a pretty common path that you'd want to look for when you're forced browsing an application. This list goes on and on and on, with all sorts of different paths, some which are highly likely to exist in most applications. But forced browsing is just brute force. Make as many requests as possible and see what comes back. And lists like this tend to be built up from real live web applications, so they do actually have some practical history. These can be very extensive. If we jump down to the end of this file, we can see that there are nearly 142,000 rows in here. So if we plug this into our forced browsing, that is a lot of requests to make. I want to try and demo this with some amount of brevity. So what I'm going to do is jump back into Burp, and I'm going to load in a special list that I prepared for this demo. And it's this one just up here, Hack Yourself First Paths. Now if we have a look at this list here, we can see CGI bin that we saw just before. We can see admin, which I mentioned. And of course we can see a bunch of other ones as well. That's plenty to get us started. So what I'm going to do is go up to Intruder in the navigation and start attack. Now here's where we're going to see a warning. And this is about using the free version of Burp. And the main thing here is that the attacks are time throttled. So this is going to be fine just to demonstrate the process of forced browsing. But if you do want to use this in a more real-world scenario, then the commercial version might make more sense. So let's say OK to that and we'll let it get started. And what we're seeing now is those requests going out. So there's the ones for CGI bin and admin that we saw just before. In fact, we can still see them behind the window here off to the left. Now here's the thing about forced browsing. A bunch of stuff is going to return absolutely nothing of any interest whatsoever. So for example, the CGI bin and the admin requests. They're returning 404, so they're page not found. The vast majority of results, when you're doing forced browsing reconnaissance, are going to be negative. There's going to be nothing of any interest whatsoever. However, when we see results that are an HTTP 200, so an OK status, so that is a resource actually exists there, that becomes enormously interesting. And what we're actually seeing here is several interesting results. So one of them is this help path. Now we're going to look at the help path a bit more later on. And as you'll see then, that actually gives us some pretty handy information. The next three though are particularly interesting. Backup.zip, database.zip, and database.back. Now they are pretty self-explanatory titles, and particularly when we look across at the content length, and that database.back being nearly a 7 meg file, that is very interesting information. And one of the first things I would do in a reconnaissance and footprinting exercise is have a look at what might be in that database.back file, because if it's what it sounds like, then that is going to be enormously useful information. One of the tricks with forced browsing is knowing what deserves further investigation and what is useless. Finding the 200 results is going to be one of the first places to start. And out of a potentially huge array of resources that could be tested in a forced browsing attack, and sometimes you'll see this referred to as directory busting as well. OWASP used to have a directory buster tool before it got rolled into their ZAP tool. So whether it's forced browsing or directory busting, there's going to be a heap of results, and knowing what to look for in terms of what could be genuinely useful is a great place to start. So that's forced browsing. Add that to spidering and you start to learn an awful lot about how the website works. Let's move on and have a look at another similar but different approach, and that's directory traversal. Let's now talk about an approach that can be very, very effective at finding not just information about the way the site is put together, but potentially some very serious internal information not just on the app itself, but on the host machine as well. Take a look at the URL in this browser. Now the first thing you'll see is that this is running on local.hackyourselffirst.troyhunt.com. So this is actually my local instance of the application. And the reason I'm showing you this on my local instance and I'm not running it on the remote instance is that what we're about to do can be particularly malicious, and I'm not inclined to put this code in a production environment that, even though it's there to test security on, I don't particularly want anyone to be able to do what we're about to do in an environment where I do want to keep the app alive. So look further at the URL, and in particular the query string. File name equals, and then there's a file name that's a .log file. And indeed we are looking at what appears to be an IIS log file in front of us. Now this is a pretty typical pattern where you'll see a file name passed as a parameter in the URL. Now here's what I want to do. I want to change this URL. And what we might do is we'll just change the file name to something like, say, foo.log. And this is interesting because what we're now seeing is an exception. Could not find the file. You won't always get an explicit exception like this bubble up to the user interface, but this makes it quite easy to see what's going on. And clearly it's looking for a file called foo.log that it can't find. So as we change the value of this file name parameter, the application is actually looking for a different file. That then begs the question, what else could we change this to? So it looks like we're in the secret report folder. What if we did this? I'm going to paste in a path from my clipboard. Have a look at what's happening here. It's going up a directory, up another directory, and then it's requesting web.config. Let's load that. It looks like we've got an empty screen, but the web.config is an XML file, and it's an XML file used in ASP.NET web applications that contains all the configuration of the app. Things like connection strings, API keys, really sensitive info. Now if we hit Ctrl+U to view the source code, we can actually see the web.config. This file should never be able to be requested remotely. You should not be able to pull this out over HTTP. But because this application is taking an untrusted parameter, and we're going to talk about that in more detail in the next module, and then going to the file system and simply grabbing that file, we've got ourselves a very, very serious risk here, because this has now disclosed not just something about the internal implementation of the system, but some very sensitive data. It gets even worse though. Let's do this. I'm going to go up to the URL again, and we're going to change this path to this one. Now that's a whole lot of directory traversals. It's going up about 9 different folders, then jumping into the Windows folder, and then asking for the system.ini file. Let's run that. And here it is. It has actually pulled that file out of the system. We've been able to ask a web application to start pulling files out of the operating system folder. That is a seriously malicious attack. Now yes, it's directory traversal, and it will help you as an ethical hacker build up a very good profile, not just of the app, but of the underlying system as well. But clearly, it is in a whole other league to just spidering and forced browsing. So do be aware of this one. If you find resources that look like they're taking untrusted data to pull specific files from the file system, there may well be a directory traversal risk that could yield some very, very useful information. The next reconnaissance and footprinting exercise I want to look at is what we refer to as banner grabbing. Now a banner is nothing more than a header returned by the server that explains what the application is actually running. So what sort of web server might it be running on? What sort of web framework could it be using? It's pretty fundamental information, and there are a number of different ways of getting these banners, not least of which is using the developer tools in your favorite browser and then using the network request tool to look at the headers in the response. But I want to show you another way. I want to just run a wget. And a wget is no more than a command that allows you to make HTTP requests. You could use something like curl to do the same thing. The reason I'm using wget from the command line though is to try and keep the browser out of the picture, to show you that this is just an HTTP request. So here's what we're going to run. Wget, we're going to use the server response switch in order to get the headers, and then here is the URL of our website. Let's run that. We can see the request going out, and now we have the response. And here are those server response headers. These are the bits of real interest though, and it's the server, which we can see is running on IIS 8.0. It's the ASP.NET MVC version, so that's the model view controller implementation from Microsoft. That's running on 5.1. The ASP.NET version that it's using is 4.0, and we've also got a lot of fidelity in the version after that, and it is running on ASP.NET. And this is just simple banner grabbing, figuring out what the application runs on. The reason why this is useful is that subsequent attacks that we mount against the system can now be targeted to ASP.NET, and in particular that version of ASP.NET and that version of ASP.NET MVC. So this helps you, as an ethical hacker, narrow down your focus, and in a case like this, probably not worry too much about the typical PHP attacks, and instead focus on the ones that might specifically target Microsoft's framework. So that's banner grabbing with wget. Let's now move on and start to take a look at some server fingerprinting. I want to now take a look at server fingerprinting, and this is going to go a step further than just banner grabbing, because when we talk about fingerprinting, we're talking about drawing conclusions about what the server may be running, well and truly beyond what it is explicitly telling us. Now to do this, I'm using Nmap. And Nmap is very basic to use in this way. What I'm going to do this time is set the target to troyhunt.com. So I'm actually going to run an Nmap fingerprint scan on my blog, because the results are a little bit more interesting, and you'll see why in just a moment. When I enter troyhunt.com in the target, it's going to pre-populate the command. And the only thing that I've added in here is the -O switch, which is going to give us OS detection as well. But basically, this is it. It's a very simple setup. So let's now go and actually run that scan. So Nmap is going to go out and start probing this website. Not just with HTTP requests, you can see here that it's also doing things like pings, and it's doing a bunch of DNS resolution and some checks there. And further to that, it is looking at some open ports. So it's finding port 80 and port 443, which we'd expect because they're HTTP and HTTPS, so very common ports to have open on a website. We can also see it now initiating OS detection as trying and retrying and running some trace routes and other tests. So the point is that Nmap does have a whole suite of tricks that it can use to try and discover what's going on the site. So we can now see it's finished. We see an Nmap done message down the bottom. We can see a whole bunch of diagnostic information out of the scan. Let's now go and have a look at the other tabs. So we'll start with the ports on the host. As I mentioned before, it found port 80 and port 443 open. Now I run troyhunt.com on Google's Blogger service at the moment. And that's what makes a scan for my website a little more interesting because Blogger returns quite a bit more information than some other web servers. Now if we jump over to the topology tab, we can see the trace route from my local machine, so where that request has gone out, all the hops it's hit before it's landed at my site. I'm particularly interested in the host details in this reconnaissance and footprinting module, because what I really want to learn about is attributes of the server. And obviously here we start to get quite a lot more information. Now one of the things that's found here is the host name of the machine that this is running on. So that could be quite useful information depending on the type of attack you're attempting to mount. As we go down and expand some of these, we can see things like the difficulty of predicting TCP sequences. If that's a foreign concept, go and have a look at my ethical hacking session hijacking module, where I talk about why predicting TCP sequences is useful. As you can see here, good luck doing that when you're talking to Google Blogger. So that's server fingerprinting. A lot of information just simply by typing in a target and letting Nmap run. And again, all of this is just about building up this broader knowledge of how the application is put together, so that as an ethical hacker, you can narrow your focus and concentrate on the aspects of the application that are most likely to yield productive results based on what the site is running on. The next reconnaissance and footprinting approach I'd like to show you is how we can discover development artifacts. And I'll show you exactly what I mean by a development artifact in just a moment. Now the tool I've decided to use for this is Acunetics. And Acunetics is a very similar class of tool to NetSparker that we saw at the start of this module. So that is, it's dynamic analysis that takes a URL and then it goes away and finds as many risks as it possibly can. So here's how Acunetics works. I've got the website URL already populated here in the dialog box. We're going to say next to that. We'll take all the defaults on this screen. So next again. Now it's doing a quick lookup and then it gives us a bit of information about the site that we're going to scan. So it's found that it's running on an IIS web server on Windows and it's suggesting that the scan is optimized for ASP.NET. That sounds just fine. We're going to accept that, move on to the next screen. We won't bother setting up any forms authentication here, but it's worthwhile pointing out that both NetSparker and Acunetics can be configured to authenticate to the target site as well. So you can test features that would normally only be accessible to a logged in user. So we're going to go next to that as well, and then finish and let the scan start. Now, like NetSparker, this takes a long time to run because it does make an awfully large number of requests. So I'm going to let that go and then we'll come back and continue on once it's finished. And here we go. The scan has now finished. And the first thing I want to look at is the web scanner results. and it has found a whole bunch of different risks. Very similar to NetSparker, lots of different findings, which you'd expect on a site which is intentionally designed to be insecure. What I really want to look at though is this finding over here about a Git repository being found. And in fact, if we expand out this tree a little bit and we have a look at specifically what it's found, over on the right hand side of the page, we can see that Git files were found at /.git/config. Now Git is a version control system. It versions source code, and source code has all sorts of useful things in it. And this website is serving up a Git repository. So as an ethical hacker, we could pull down this repository, which is accessible over HTTP, Acunetics has confirmed that for us, and start inspecting the contents of that repository. Look at the revision history, who's written code, what are their comments about the code, when did they write it, and of course what is the code itself. Not only would that allow us, with our attacker hats on, to start finding vulnerabilities in the implementation, very often these repositories also include sensitive data. So things like API keys or other credentials which could then be used to compromise the application. Source control is an absolute treasure trove of information when you're looking to exploit a system. And tools like this make it enormously easy to find when a source control repository exists in a publicly retrievable fashion. Another thing that can be really useful for reconnaissance and footprinting is looking at automatically generated resources that help explain how the site is put together. Now, web services in particular do a very good job of documentation. And when I talk about web services, I'm talking about APIs. So programmable interfaces which are designed to be consumed by other programs. Now, often these are thought of as a different class of application to a web application, but really they're the same thing. Resources requested over HTTP that process input and return results. The main difference is that they're not necessarily intended to be human readable. Now, one very common pattern of web services, albeit one that is now starting to become a bit legacy, is a WSDL, a Web Services Definition Language. And that's what we're looking at here. And a WSDL explains the methods that a service implements. So what we're actually looking at here is a whole bunch of XML that tells you exactly how to consume this service. Now, this is a public service intended to be publicly consumable, so there's nothing wrong with showing it here. But you will often find services that disclose how they're implemented in ways that were never intentional. Now, we can get a more human-readable version of this WSDL just by taking out the query string. And this is a pattern that Microsoft implements in their frameworks, which then gives you this nice human-readable definition here. And this service is all about the weather. So one method to get a bunch of cities by country, and another to get the weather. So we can drill down into a service like this one for get weather, and see exactly how it works. So for example, let's try this. And now we'll invoke the service, and here is the weather. Again, it's a bunch of XML that's not really designed to be human readable, but we can still get a bit of a sense of what's going on here. Now, the weather is not particularly sensitive. We're not too worried about it, particularly when the service is designed to be public. But looking for WSDLs in an application that you're testing can be a really effective way of finding risks, particularly if they're documenting features that really should remain hidden. So do look for these. Let me show you another one, a more modern implementation to look for. This is Microsoft's implementation of help pages for their Web API framework. And it's a very similar concept to what we just saw with the WSDL and the more human-readable version of it. Now, this one is a self-documenting API. So it looks at the Web API implementation and then generates this document at the /help path. So looking for a /help can yield some really interesting results. So for example, have a look at this second one, admin API. And it's documented right here. We can see that we can make a GET request to API/admin/users. In fact, it's so well documented, let's have a look at that method right here. So here's exactly what it will return. User ID, email address, first name, last name, whether or not they're an admin, and the password. It'll even give us a nice JSON representation of what the response looks like. If you were to stumble across this in your testing, the very next thing you do is start running this API and seeing what sort of passwords you could pull out of the system. As contrived as this example might look, I have seen this in production systems. It happens. People create these APIs without realizing that they are readily discoverable, and they consequently don't correctly secure them. But when you've got documentation like WSDLs and help files like this one here, automatically generated, it's very trivial indeed for you to go and find them. In the opening module of this course, I mentioned CVEs, or in other words, publicly documented risks in frameworks. And in fact, the context was that 99.9% of the exploited vulnerabilities in Verizon's 2015 Data Breach Investigations report were compromised more than a year after the CVE was published. And you can find those CVEs right here. Now let me give you an example, and I'm going to use this example both here and in the next clip as well. Let's jump over to the search section here. And what I would like to search for is Drupal. Now Drupal, like most popular frameworks, has had a number of serious vulnerabilities over the years. And in fact, what I'd like to do is just have a look at all the Drupal CVE entries. And we are going to see a comprehensive list, 953 of them as at the time of recording. Now, if you had been doing reconnaissance and footprinting of an application and you discovered, using the techniques we've already covered in this module, that it was running on Drupal, this would be a good first stop. So going here, looking at the list of CVEs and finding what vulnerabilities the version of Drupal you're looking at might have. So let me give you a really good example of a serious one. I'm going to scroll down to the CVE from 2014 that ends in 3704. Now this was a really serious one. Let's drill down into it and see what the problem was. What this actually was a SQL injection attack. A very serious SQL injection attack. In fact, it was so serious that Drupal advised if you had not patched your systems within 7 hours, you had to consider them compromised. 7 hours, that's less than a good night's sleep. And that information was available here. Not only is it available here, but we can drill down into resources such as the exploit DB and actually find exactly how to exploit the vulnerability. So here it is. Here's the proof of concept code. You can take this, run it against a Drupal 7 implementation that is not patched against this CVE, and launch your own SQL injection attack. And SQL injection is about as serious as security risks get. So hopefully this shows you just how powerful a good bit of reconnaissance and footprinting can then be when it's used in the context of actually discovering risks in that specific environment that you've been mapping. The last thing I want to do in this module is go and look at another way to find systems at risk. Let's go and look at Shodan. We just saw a really serious risk in Drupal 7, and it had a published CVE and an entry in the exploit database that explains exactly how to exploit that system. Now, in your ethical hacking, you'll probably be coming from the perspective of testing an existing system, a known system, and looking to see if it's properly secured against risks. But just for context, there are those who deliberately seek out other systems that may be at risk, not necessarily the ones that they're responsible for. And once they understand that a risk like SQL injection exists in a framework like Drupal, it's very easy to use a tool like Shodan to then go and find at-risk systems. So let's try this. I'm just going to search for Drupal 7. Now what Shodan has done is it's gone away and looked for sites that are returning the Drupal 7 banner. So we looked at banner grabbing a little bit earlier on with wget. And what we're seeing here is exactly what you'd get in a banner grabbing exercise. So these are the response headers that the servers are sending. And we've found a huge number of results for Drupal 7. Now, it doesn't necessarily tell us whether they're patched or not. But had you done this in the very early hours after that vulnerability was disclosed, you'd experience a very high hit rate of finding servers that weren't protected. So whilst this may not be the normal approach you'd take in ethical hacking, I did want to point this out just to make it clear how easy it can be to discover at-risk systems using free, publicly available tools. Let's summarize the module. And one thing that should now be abundantly clear is that you can get a lot of information out of reconnaissance and footprinting. We looked at everything from publicly disclosed sitemaps through to forced browsing through to directory traversal. And that's just building up the site structure. Then there's banner grabbing, server fingerprinting, finding development artifacts on the website itself. Not to mention looking at documentation generated by API frameworks such as WSDLs and other help files. Then of course, once you identify that framework, using resources like CVEs to learn how to exploit it makes that reconnaissance and footprinting exercise extremely valuable. There are clearly a number of automated tools to help you do this. NetSparker, Burp Suite, Nmap, Akinetics, and even just a simple wget. All of these tools can help you discover information about the environment, which will then aid you in your ethical hacking exercises. So using these tools to map out the web app can give you a real advantage when it comes to actually identifying viable exploits against the app. So use this as the first part of your ethical hacking activities. Go through and discover as much as you can about the target using tools such as we've seen here in this module, and it will greatly accelerate your efforts as an ethical hacker. Now that we've learned how to map out the way the application functions, let's move on to the next module and start looking at tampering of untrusted data. I want to start here, and it's with the OWASP Top 10. Now, as you can see here, OWASP is the Open Web Application Security Project, and they create a publication known as the Top 10, which, as you can also see here, is the 10 most critical web application security risks. Now, every few years they release one of these documents, and they've become the canonical reference for web application security risks. I've already got a number of different Pluralsight courses on the Top 10, so if it's an unfamiliar concept to you, go and check out one like Web Security in the OWASP Top 10, the big picture. Or if you live in an ASP.NET world, check out the OWASP Top 10 Web Application Security Risks for ASP.NET. Now, the reason I'm showing OWASP here is because as we proceed through this course, and I discuss things specific to hacking web applications, which are already captured in the OWASP Top 10, we're going to take just a moment to look at how OWASP describes the risk, because I want to make sure we can relate that risk back to this canonical industry definition of why it's so important. Now, what you'll find as we scroll down through this OWASP Top 10 is that the top 10 risks themselves probably look quite familiar. We've got injection here, which frequently refers to SQL injection. We're going to look at broken authentication as we go through this course. There's session management, which I already have an ethical hacking course out on. We'll look at cross-site scripting in this course. We'll also look at insecure direct object references and security misconfiguration and sensitive data exposure. We're going to cover missing function level access controls, cross-site request forgery, and also unvalidated redirects and forwards. So the top 10 is actually going to feature quite heavily through the remaining modules, just simply because OWASP aligns so well to what ethical hacking refers to as hacking web applications. So that's just a quick intro on OWASP. Let's now move on and take a look at exactly what I mean by untrusted data. The definition of untrusted data is an important concept to get right before we move on and start exploiting risks. And really, when I talk about untrusted data, I'm talking about something that comes from an externality. So something outside the direct control of the system, something that we have to assume might be tampered with in such a way that it attempts to do something malicious. So here's a good example, the request body. So this is what is sent to the server when a form is posted. So think about, say, a registration form. The name, the email address, the password. All of that is part of the request body. And all of that can be manipulated by the attacker. They can change any of those values. Now, not only can they change it in the web form itself, but they can also reconstruct their own HTTP request entirely independently of the browser and change these values to whatever they want them to be. That includes hidden form values too, and we're going to look at hidden field tampering in this module. Another source of untrusted data is request headers. Now, the request header has everything from the user agent, so what browser it is the user is using, to the language that they prefer, and even where they've just come from in the referrer header. All of this can be modified by an attacker. It is untrusted data. It gets sent to the system from an externality, whether that be the browser or a custom HTTP request that the attacker may have coded up, and the request headers can be set to anything that the attacker wants. It can include a malicious payload. So you cannot trust request headers. It is untrusted data. Another probably more obvious source of untrusted data is the query string. You can change a query string to whatever value you would like it to be. In the introductory module, we looked at how a query string could get a specific widget. You could change it so that it gets another widget. You could also change it so that it possibly mounts a SQL injection attack. It's untrusted data. The attacker can do whatever they want with that query string. The trick then becomes, how does the web application handle it when the query string is malicious? We also looked at routing in the introductory module. So another way of defining parameters which we might have otherwise put in a query string. Now, an attacker can modify the route because it's just a URL. So they could change that request to widget number 1 in the route, and they could change it to something like a cross-site scripting attack. Whether or not that attack is actually successful is entirely dependent on how the web application parses that untrusted data, the route in the URL. So that's another perfectly viable way of passing untrusted and potentially malicious data over to the server. Another source of untrusted data again is changing the HTTP verb. Now, I also touched on that in the introductory module. And in fact, I mentioned that in a very semantic HTTP implementation, you might support something like the delete verb in order to actually delete a resource. There's nothing to stop the attacker from changing a get verb for a specific resource to a delete verb. The question, of course, is what does the application do if an attacker is trying to delete a resource that they're not authorized to delete? That's the trick with untrusted data. You can't change the fact that attackers can manipulate untrusted data. All you can do is change how the web app responds when an attack comes in. And finally, external services. So if a web app is calling out to a service run by some external asset, the data that's returned from that service is untrusted. It could be malicious. So for example, a website makes a request to a web service on a completely different application. That application returns a malicious payload in the response, and the first application consumes that, and then possibly exposes, say, a persistent cross-site scripting attack. I'm actually going to give you an example of precisely that later on in this course, where persistent cross-site scripting attacks have been embedded into DNS records, and then the application consuming the external service and pulling in that untrusted data hasn't properly catered for the fact that it could indeed be malicious. Now, one other quick note on this as well. Defenses like SSL, so serving the content over a secure HTTPS connection, do not help one bit with this style of attack. An attacker can still quite happily modify, say, the query string of an application over an HTTPS request. That attack will still go through to the server. It's just that it will go through in a fashion that then can't be intercepted by another attacker. And then anything that the response returns also can't be intercepted. It's still an attack, it's still just as effective, and transport layer security, which we will look at in more detail later on in this course, does not provide any defenses whatsoever against these attacks. So now that we've covered that, let's move on and start taking a look at an actual parameter tampering demo. I want to start by showing you a fundamentally straightforward parameter tampering demo. And by doing this demo, we're actually going to cover a number of the concepts we've seen already, plus a few new ones as well. Now here's what I'm going to do. I am presently logged into this website. We can see Hello Troy there in the navigation bar. I'm going to click on View the GTR. And what you'll see here when I load up the GTR is that you've already voted for the GTR. I can't vote again. The whole premise of this application is that you can vote once. However, if I go back and then I scroll down and we view the Pagani's, there's one Pagani, it's the way error. We'll view that, and now we can see a vote button where we didn't have one before. So this is the access control in practice. If you voted for the car, no button. If you haven't, then you get the button. Now I'm going to click this button and send a vote in just a moment. But before I do that, I want to jump over to Fiddler. And Fiddler is an HTTP proxy. It's a very popular tool amongst software developers for debugging their applications. But Fiddler is also enormously useful for testing the security position of web applications. So here's how Fiddler works. When you fire it up, it will set your machine to begin proxying requests through it. All I need to do now is go down and start capturing by clicking in this bottom left-hand box. Now that it's capturing, I'm going to Alt-Tab over to the web application. I'm going to snap it over to the right side of the screen so we can see what happens in Fiddler just behind it. Now I'm going to click the vote button, leave a quick message, vote, and now we can see that request appear in Fiddler off to the left-hand side of the screen. Let me now jump back over to Fiddler, and I'm going to stop capturing because I don't want to see any other requests that the machine is generating that go out via the Fiddler proxy. Let's now go and take a look at this request I just captured. So I'm going to go up and select it, and then over to the right-hand side of the screen, we'll see the Inspector tab is highlighted. And the Inspector describes the request. Within Inspectors, we're on the Headers option at the moment, so we can see that it was a POST request to /API/vote. Now because it's a POST request, it's going to have a request body. So we can go over and look at the web forms here, and we'll see that there are 3 pieces of data sent in the request body. The user ID, the supercar ID, and the comments. And there's that nice comment I just entered. So what we're looking at here is exactly what was sent in that request. Now here's what I want to do. Let's jump back over to the web app for a moment. We can maximize that again. And if I reload the page just to confirm, we can see the text that says you've already voted for the way error. There are 4 votes of 21 total votes in the system. And if we scroll down a little bit, we can see my comment there that says nice. And we can see that it was definitely me that made that comment. It's got my name attached to it. But let's do this. Let's play with a bit of parameter tampering and see if we can get someone else to vote for this car. So I'm going to switch back over to Fiddler, and I'm going to jump over to the Composer tab. I'm now going to grab that request that I made just before and drop it here into this Composer tab. Now down the bottom we can see the request body, user ID, supercar ID, and comments. I'd like to pick another user. Let's pick user number 10 instead. So I've just manually changed that parameter value. I have tampered with the parameter. And not only can I tamper with this parameter, I can also tamper with the comment as well. So let's make this very nice instead. Now there shouldn't be anything wrong with tampering with the comments. So comments are intended to be untrusted data. People should be able to enter their own. But tampering with the user ID is not something that you should be able to do. You shouldn't be able to vote on behalf of somebody else. Let's now go up and actually execute this request. We see it appear on the left-hand side of the screen, and now it's completed successfully. I'm going to Alt-Tab back over to the web application, F5 to reload, and now we see a new comment further down the screen from Nico Rosberg. Very nice. So Nico must be the person that owns user ID number 10. And by changing that ID to Nico's ID, so tampering with the untrusted data, I've just caused the application to do something that it is not intended to do. I have voted on behalf of somebody else. So this is a great example of parameter tampering. And not only does it show the ability to change parameters that are submitted to the web application and get it to do something that it's not intended to do, but we didn't even use the browser. We took that client out of the picture and we went to the Fiddler HTTP proxy and demonstrated how, at the end of the day, it's just an HTTP request. It doesn't matter which client submits it. If it's constructed in such a way that the web application recognizes it, you can submit it through to the server and cause it to do something that it wasn't designed to do. So that's an intro to parameter tampering. Let's now move on and start looking at different ways of tampering with parameters. And the next thing I want to look at is tampering with hidden fields. The next tampering of untrusted data example that I'd like to look at is modifying hidden form values. Now, hidden form values are nothing more than an HTML tag that isn't visible in the browser yet is submitted as part of the request body. They're commonly used to persist data between requests. So if you had a piece of data on one page that you didn't necessarily want to show the user, but you wanted to make accessible on the next page after submitting the form, then a hidden form value would be a way of achieving that objective. Now, it's very easy to find hidden form values just by viewing the source code of the page, but we can also use the browser tools to go down and right-click on an element, inspect the element, and then have a look at the source code. And you may well find something that looks like this. An input field called isAdmin. Now, when I see something like this, I become enormously curious, because the way it looks is that if we were to change the value of this form field, and remember, this is untrusted data, it doesn't matter that it's hidden, we can go and modify this to our own value. So what I'm curious about is, can we change the value of this hidden form field such that it makes me an admin? Let's give it a go. I'm going to right-click and edit as HTML. I'm then going to go through and change the value here, and I'm going to make this value true. I'm going to click back up in the browser window, scroll down a little bit, and hit the Save button. And now we see something curious. We have an admin link in the navigation bar. Let me hit F12 to close the developer tools, and we'll go and take a look at what we've got up here. There's a Manage Users link. This does look very enticing. Let's go and have a look at this one. And here we have a list of all the users in the system and their passwords. Now, clearly there are multiple things wrong with what's going on here, but the point I really want to make is that it's very easy to simply change the value of a hidden field. And the web application needs to work on the assumption that attackers will do just that. A canonical example of where this is risky is in a shopping application where a hidden field might persist the price of the item being purchased. If an attacker can modify that hidden field and change the value of the product, does that then persist through to the checkout and they pay what would probably be less for the product because they've tampered with the field? That would be a very effective attack. I've also seen systems that do things like persist the internal application connection string So the one that actually connects the app to the database in a hidden field. In fact, I've seen it in the view state of an ASP.NET application, which is persisted as that hidden field. This does sometimes happen. People either put sensitive data in hidden fields or data in hidden fields that can be modified to cause the application to do something completely different to what it was designed to do. So you want to pay very close attention to hidden form fields on pages. Let's now move on and look at a different type of tampering attack, and that's a mass assignment attack. I want to look at a different class of parameter tampering attack now, and it's a mass assignment attack. And the best way to explain how this works is to just show you. So here's what I'm going to do. I'm back on this user profile page. So this is the one where we just manipulated the hidden field to make me an admin. Now what I've done is reverted that change. I'm no longer an admin. We don't see admin up there in the navigation bar. And if I go and inspect the hidden fields here, we'll find that there is no longer a field for isAdmin. So I can't just go and tamper with the form like I did before, at least not in the browser. Now here's what I want to do. I'm going to hit F12 to close the developer tools, and I'm going to snap the browser window over to the right of the screen. I've got Fiddler running behind it. Now all I'm going to do is just save this form. And as I do that, you can see the request appear in Fiddler. In fact, you can see 3 requests. So the first request we can see to the user profile, that has an HTTP 302 result, which is a temporary redirect. So it sends the browser to another location. The second request is the location it was redirected to. And all that is a message that says, hey, your profile has been updated. That's the one we see in the browser to the right. And then the third one is a Google Analytics request. So nothing functional to do with this site, it's just tracking requests. Let's now jump over to Fiddler and I'm going to stop capturing. Now here's what I want to do. I'm going to go up and grab that first request and drag it onto the Composer window. If we have a look at the request body down at the bottom right hand part of the screen, we can see that there is no isAdmin field. There's a user ID, a first name, and a last name. That's all that goes in the request body. But what if we were to add one? So what if we went over to here and added isAdmin equals true? Just like that. So keeping in mind that this didn't exist already, not in this example, there was no hidden field for isAdmin. All we've done is gone and added it ourselves. Let's now go and execute that request. And Fiddler does the same thing again, sends the request and then redirects. Now let's go back to the browser. I'm going to maximize the window and then F5 to refresh. And now I have the admin link back in the navigation bar. How did this happen? There wasn't an isAdmin field in the page. So what made this possible? Well, the concept of a mass assignment attack is that very often a web form is implementing what we call model binding. So it's taking a model, which in this case is a profile, and it's automatically binding any attributes that are sent in the post request to the model in the database. So even though the web application may not explicitly be sending that isAdmin flag in the request, the framework is automatically persisting any attributes that match the model from the HTTP request all the way down to the database. You see this happen a lot in more modern frameworks that make things easy for developers by automating this model persistence. So what is designed to be a convenience, and certainly it does make the process of building software easier, can actually be a risk if it's just automatically persisting every single attribute of the entity that's sent in the request. So that is precisely what a mass assignment attack is, taking that mass of fields and assigning them to the underlying model. Now this has also been used to great effect in the wild. In fact, back in 2012, we saw a proof of concept against GitHub where someone managed to add their own SSH keys to other repositories because of a mass assignment risk. And in that example, it was a vulnerability in the Ruby on Rails implementation. So this is a real risk, and it's a great example of just one of the flavors of tampering with untrusted data in order to exploit a system. Let's take a look at another attack involving untrusted data. And this time, I want to look at cookie poisoning. Now, a cookie is untrusted data because it's part of the request header. So when you make a request for a website, any cookies which are valid for that domain are automatically sent. Now you can hit F12 to jump into the developer tools, jump over to resources, down into cookies, and then look at the domain that we're interested in. And here are all the cookies that are automatically getting sent with every request that we make to hackyourselffirst.troyhunt.com. These cookies are persisted in the browser. The browser is automatically sending them, and we can modify them at multiple points. So we could create our own HTTP request using something like wget, or using a tool like Fiddler, or we could just simply modify the cookie values in the browser itself. And this is what I want to do here, because there's one cookie in particular that I find quite interesting, and it's this one. It's this isAdmin flag again, and it's set to false. But as we've seen in the previous couple of clips, things get a bit interesting when we make this isAdmin flag true. So let's do that. I'm going to jump over to the console, and now we can write JavaScript that will execute in the DOM of the browser for this website, so in the document object model. Now let's do this. I'm going to write document.cookie equals, and then the name of the cookie, which is isAdmin, and then I'm going to set it to true. Now I can just hit enter and it's going to execute that. So that should now have set our cookie to true. So let's go and take a look at that. We're going to go back to resources, and then in our cookies, we can see that isAdmin is now true. Let's now close the DevTools, and I'm going to click a link, which is now going to cause that cookie to be sent in the next request. So let's go over to the leaderboard. And here is my admin link in the navigation bar again. So we're back to where we were in the last couple of clips. We've exposed functionality by modifying untrusted data. The only difference is, rather than modifying a hidden field or mounting a mass assignment attack, we've simply changed this little piece of data which is persisted in the client. And that has resulted in exactly the same risk as the other parameter tampering examples. So that is cookie poisoning, changing the value of the cookie in order to give the attacker an advantage. I want to talk now about insecure direct object references. And this is where I'd like to draw an association back to OWASP. So I introduced OWASP at the start of this module, and I said that as we go through the course, I'm going to call out risks which they specifically address in their top web application security risk document. And insecure direct object references is one of them. Now, OWASP prioritized their risks based on a number of different factors, and you can see those represented in the table here. And those factors include things like the exploitability. It is easy to exploit an insecure direct object reference risk, and we're going to see just how easy in just a moment. It's also quite a common risk, and the detectability is also easy. And again, you'll see just how easy in just a moment. The impact they've classed as moderate, and it really comes down to the nature of the system. So what is the resource that the insecure direct object reference is going to expose to an attacker? This is their number 4 risk out of the top 10, so it is quite high on their list of risks. Let's jump over and do a demo so you can see just how impactful this risk can be. So back on our insecure site, what I want to do is jump up to the My Account item in the navbar and go down to Edit Profile. Now we've spent a bit of time on this page already during this module, and one thing that you may have noticed is that the URL appears to have an ID in it. So this is that very semantic routing-based URL that I spoke about in the introduction to the course. And if we have a read of it, it makes a lot of sense. This is the account for user profile number 1. Now, when you look at a pattern like this as an ethical hacker, what you should be thinking is, what would happen if I changed user profile number 1 to a different user profile? So earlier on in this module, in the first demo, I showed how we could modify the user ID parameter when we voted for a vehicle to change it from my ID, number 1, to ID number 10, which was Nico Rosberg. Let's see if that works here as well. Let's change 1 to 10. And here we have Nico Rosberg again. So what we've been able to do is directly reference the internal ID for this user profile, ID number 10, and that has pulled back his record. There is a lack of access control here. So at no point has the system said, hey, should Troy, who is presently logged on now, you can see my name there in the navigation bar, have access to user profile number 10. That bit's been missing. So the first thing is, obviously this resource can display other people's profiles. That in itself is a direct object reference risk. That is, of course, assuming that the system is not designed to do that. You probably shouldn't be able to edit other people's profiles. But let's actually validate that. Can we go and change Nico to Nico 2? Let's now save his profile. And it looks like the profile has been updated. Earlier on, we voted on the Pagani. Let's go and see if Nico is still Nico, or if Nico is now Nico 2. So we'll go up to the leaderboard, down to the Pagani, and scroll down to the comments, and now we have Nico 2 Rosberg. So that change has actually been persisted in the database, and we have now changed someone else's name due to an insecure direct object reference risk. So you can see now why OWASP says the detectability is easy and the exploitability is easy, because all we've done is changed an ID in the URL. And this is a risk which we have seen many times on the web. And a canonical example of that is banks with account numbers in the URL. And all you do is you just change the account number to someone else's, and suddenly you pull up their banking data. That has happened multiple times with high-profile banks. So it is a very real-world risk. We've just exploited the system via multiple different examples of tampering with untrusted data. So let's now spend a bit of time talking about how to defend against this attack. And the first rule of protecting against the risk of untrusted data is this: don't trust anything. You need to expect that every piece of untrusted data is malicious. And that means applying some fundamental controls to all of these external inputs. So let's talk about what some of those are. So I'm going to cover 4 different ways of defending against tampering. And the first one is what I just touched on the previous slide. Always assume malicious intent. So for example, before, when I showed how I could change the user ID from my own to Nico Rosberg's and vote on the vehicle on his behalf, you need to assume that that ID will be modified because it is untrusted data. So there has to be an independent verification process of what the identity is. And the right way to do that would be to look at the authentication token of the user. Now, I talk a lot more about how authentication tokens work in ethical hacking session hijacking. And that course explains how the token should be a cryptographically strong identifier, and we use that to identify the user, not just some integer which is passed through as untrusted data. The next thing is, we always have to verify on the server. So think about the hidden form example. I changed the user ID to Nico's, and the server never made sure that the person sending that vote was actually the same person whose user ID was sent. It just relied entirely on the untrusted data. It trusted the client. It didn't independently say, is this actually the user trying to vote? So verification on the server is absolutely critical because you can't trust the other data that comes to the server. So verification on the server is critical because you can't trust the untrusted data that comes via the HTTP request. Another thing to be really conscious of is client persistence. It is enormously dangerous. So we saw that hidden field with the isAdmin flag. We know now that you can't trust that somebody else could modify it. And persisting anything via client constructs, not just hidden fields, but things like cookies as well, and we use the same attack with the cookie, is enormously risky. Now you can use approaches like a MAC, a message authentication code, to persist data on the client and then ensure that it hasn't been tampered with once it comes back to the server. But certainly, simply persisting a value like that isAdmin flag anywhere where it can be tampered with is enormously dangerous. And finally, whitelisting allowable behaviors. Now this is a pretty fundamental principle when it comes to dealing with untrusted data. In the example before with the mass assignment attack, we allowed the application to save the isAdmin flag even though it should never have been sent back to the change profile page. What that resource really needs to do is to say these are the attributes that we're happy to bind. You can still use these nice modern model binding constructs, but you have to be explicit about which attributes of the model you actually want to persist and bind from untrusted data. Now you'll also see this objective, the whitelisting of allowable behaviors, repeated at multiple other times throughout this course. You're going to see it when we look at cross-site scripting, and if you've gone and done my ethical hacking SQL injection course, then you would have also seen it there. And this is really a very, very fundamental tenet of information security. Be crystal clear about what it is you are going to accept from the user and what it is allowed to do. If it doesn't meet that criteria, then reject the request. So there are 4 fundamental things to think about when it comes to the risk of tampering of untrusted data. Let's now move on and summarize the module. Let's summarize the module. And one of the first things I showed was just how many inputs there are into the system that you have to consider as untrusted. So that included everything from the request body to the request headers, the query string, the URL, even the HTTP verb and external services. All of these inputs come from externalities, they're all untrusted, and you have to assume that every single one of them has been tampered with. Now, when we talk about tampering, there are multiple points where that tampering can occur. So we tampered with the request body in Fiddler. We tampered with a hidden form in the browser. We tampered with cookies. We tampered with insecure direct object references. There are plenty of points where untrusted data can be modified such that its intent becomes malicious. And that always has to be the assumption as well. Assume malice on every single one of those classes of untrusted data. Validate it accordingly. Make sure that no matter what that external party changes the data to be, that it cannot cause the system to function outside its intended behavior. Tampering of untrusted data is often a fundamentally simple attack, and it can have dire consequences. Now that we've established that, let's move on to the next module and start talking about attacks involving the client. Cross-site scripting, or as we also know it, XSS, is an enormously important risk. In fact, it's up there in the number 3 position in the OWASP top 10 web application security risks. And we're looking at how they describe the risk right here. And the 2 things that really stand out here is number 1, the prevalence. It is very widespread. XSS is all over the place. And not only is it all over the place, but it's very easy to detect. So that means it's very easy for attackers to detect the presence of an XSS risk. It also means it's very easy for you as an ethical hacker to find it yourself. And we're going to look at how to do that in this module. So that's just a quick introduction to put XSS into context and establish just how important it really is. Let's now move on and actually mount an XSS attack. We're going to look at a couple of different styles of XSS attack in this module. And the first one is reflected cross-site scripting. And I want to give you an example of what I mean by reflection, because that's a key concept here. So let's do this. I'm going to go up to the search box and I'm going to search for Pluralsight. Now there are no matches for the word Pluralsight. We have no supercards with the word Pluralsight in them. But that's fine, because what I'm really interested in here is the way the search term has been reflected. And what I mean by reflected is that we can see the search term appear in the response in two different places. So we can see it in the original search box, and we can also see it in that heading, you searched for Pluralsight. So this is reflection. You give something to the system, and then the system shows it back to you in the response. Now the interesting thing here is that the something that you give the system is untrusted data. And we now know that we can tamper with untrusted data and potentially cause the system to do unexpected things. Just to illustrate precisely how this reflection works, if I press Ctrl-U to view the source code of this page, and then I do a search for Pluralsight, we can see one result here on line 55, so that's the heading, and then we can see another result down here on line 81, which is where the search term was reflected back into the search box itself. So the point again is that we can give the system data, and then the system will write the data into the source code. Now let's close that tab. And what I want to do now is mount my cross-site scripting attack. Now you'll notice here that I'm logged in. It says Hello Troy up there in the navigation bar. And what this attack is going to do is take advantage of my authenticated state. So I am the victim. Now in the scenario that we're going to run here, someone has sent me a link. That's all it is, just a URL. It could be via social media, it could be via email. The channel doesn't really matter so much. The important thing is that I'm going to follow a URL that someone has sent me. So here's the URL that I've been sent, the malicious URL with the reflected cross-site scripting attack in it. I'm going to load this address and see what happens. And here we go. Nothing interesting to see here at all. Apparently, no results found for the search. Now, what you can't immediately see here, and certainly what the victim can't immediately see, is that my authentication token, the thing that keeps me logged into the website as I browse around, was just stolen by the attacker. In fact, the only thing that looks at all odd on this screen is the broken image off to the left. And I've actually left that there intentionally just to give some little indicator of what's going on. Let me explain how this works. Anything that we pass in the URL as part of the search term query string, so you can see it up there, gets reflected in the source code of the page. We saw that earlier on when I searched for Pluralsight. Now what I've done is reflected some JavaScript, and that JavaScript adds an image to the page. Now the source of that image is what's interesting, and a really good way to show you what that looks like is if I press F12 to open my developer tools, I'm on the network tab. Now if I reload the page, we're going to see this request go back out. And what we can see towards the bottom of this set of requests is one that goes to the domain evilcyberhacker.com. That's my domain. I use it for demonstrations like this. And clearly it is an evil cyber hacker's domain. And the path that is being requested is log cookies with the query string of cookies equals, and then we can see some other text off the end of that. Let's drill down on this request and take a closer look at the URL. So here you can see the whole thing. And what we're actually seeing is a number of different cookies. So there's one here which is visit start. So that's a cookie that gets set every time the session begins. We can see an affinity cookie here. Azure sets this in order to implement sticky sessions. But most importantly is that we can see an auth cookie. Now I talk extensively about auth cookies in my ethical hacking session hijacking course. And what you see in that course is that once an attacker has that auth cookie, they can go and hijack the session. They just simply recreate this cookie in their own browser. Now, why was this resource requested? So why is this URL here being requested? Well, if we go up and scroll down a little bit to look at the image and right click on that and jump into inspect element, we can see here down the bottom of the screen that the URL is actually the source of an image. So the evilcyberhacker.com address was set by the reflected cross-site scripting attack, and it included all of the cookies. So effectively, we've just sent the cookies off to that external site by defining it as the source of an image. Now we can go and have a look at how the server responded as well. I'll just right-click on the image source, open the link in a new tab, and here you can see logged your cookies. So this is actually evilcyberhacker.com that's responded. They now have my cookies. The last thing I'll do is just close that tab and then view the source code of the page. If I now do a search for Evil Cyberhacker, we'll see that untrusted data reflected once in this first location, which is where we saw Pluralsight before, it's in the heading, and a second time down here where the value of the search was set back in the text box. And this is really where the XSS attack is executing. And if we have a look at the URL, you can see precisely what the search term query string is, and I can highlight it here where it's been reflected in the source code. So it's everything from this single quote all the way through to the // towards the end of this script block. So let's talk through this logically. I've closed off the jQueryVal function and terminated that statement. That then gives me some clean air, if you like, to then write my own JavaScript. I've then declared an image and set the image source to this Evil Cyberhacker address. I'm passing a query string of log cookies, and I'm adding to that document.cookie. Now document.cookie will get all of the cookies that the client script has access to. And a little bit later on, I'm going to talk about how to prevent this style of attack from doing that. I'm then appending that image into the body. Now this is happening in the DOM, in the document object model of the browser. So it's actually the browser reading these instructions and doing this after the site already loads. I then go through and find the heading 2 tag, which is where we would normally reflect the search term. But the search term is all of this attack script. So what I've actually done is changed the value that was loaded from the server and replaced the contents of that h2 tag with nothing interesting to see here at all. I then terminate that statement, and the // is used to comment out the remaining JavaScript so that there are no errors in the browser. So there are a few different things happening here, but it is fundamentally a simple attack. Now, if you'd like to understand this in more detail, go and have a look at both that ethical hacking session hijacking course and also my Hack Yourself First course, where I go into a lot of detail on cross-site scripting. For now though, that is how a reflected cross-site scripting attack can execute. Let's now move on and take a look at a persistent cross-site scripting attack. We just looked at a reflected cross-site scripting attack. So that is one where the victim had to follow a malicious URL, and then the payload in the untrusted data was reflected back into the source code of the page. I want to show you another XSS attack though, and that's a persistent cross-site scripting attack. Now this is best demonstrated. So let's do this. I'm going to go over to the leaderboard, and then I'm going to go down and click on the Bugatti Veyron. Let's take a look at that vehicle now. It loads, and then very quickly it disappears, and we end back on evilcyberhacker.com. This is exactly the same resource that we saw just before. And in fact, the URL is the same as well. We can see the cookies reflected up there in the address bar. So how did this happen? What is the construct that made that possible? Well, if I jump back one, and then immediately after I click on the Bugatti, I hit Ctrl-U to look at the source code, and then do a find, again for Evil Cyberhacker, we can see exactly the same attack as we saw earlier appear here in the source code. Now, in a persistent cross-site scripting attack, the payload is persisted, so it exists in a data construct such as the underlying database. And in this case, what's happened is it actually appears in a comment. So someone has gone and left a comment on this website, inevitably Guido, we can see him on the line above this attack, and that comment has got the XSS payload. You wouldn't see this in the web interface because it's just a script tag, so there's nothing visibly rendered. But clearly it has been very effective. The really nasty thing about a persistent cross-site scripting attack is that you don't have to engineer the victim into following a malicious link. They just go to the site and use it as designed. And not only that, but the scope of victims now dramatically increases because anyone who goes to this resource gets hit with the cross-site scripting attack. Now this goes back to the previous module when I defined untrusted data, and I said that one of the sources of untrusted data is the request body. And what's happened here is that that request body, so that is the body that came when the comment was left on the vehicle, gets persisted. Now while we're talking about persistent cross-site scripting, in that previous module I also said that a source of untrusted data was external services. And I'd like to go and give you an example right now of what that looks like. In 2014, a security researcher wanted to demonstrate the risk of persistent cross-site scripting when the attack payload was persisted via DNS records. So that is, they created a domain and they added a DNS record, such as a TXT record, that had cross-site scripting in the value of the record. The researcher made a video of what this meant when a site designed to show DNS records didn't properly handle untrusted data from an external service. The best way to see how this works is just to watch this video that he prepared.
Con los terroristas.
Harlem Shake.
That is quite an impactful demo, and what it shows is that the researcher was able to get a site to run both CSS and external media simply by going to this Whois search site and loading up his domain name. So what he had actually entered into his DNS records persisted all the way through to the Whois site, came back out in the response when his website was shown, and executed in the browser. Now playing the Harlem Shake is really just a proof. Clearly there's not much of an upside for an attacker in getting the browser to dance around this way. But what it shows is that he was able to run this external arbitrary script in this particular Whois website. Now there have been many similar demos in the past, and in fact in my Pluralsight course on Introduction to Browser Security Headers, I show another video where someone demonstrated the ability to get Dutch banks to do this via reflected XSS. In that course, I also show how to prevent this style of attack, or indeed ones that are genuinely malicious, using the Content Security Policy browser header. So that one's well worth checking out. For now though, we've seen both reflected and persistent cross-site scripting. Let's go on and talk about how to actually defend against this attack, and look at some of the countermeasures we can use to stop it dead in its tracks. Now that we've seen a couple of different styles of XSS attack, both reflected XSS and persistent XSS, I want to touch briefly on the mechanisms to defend against the risk. So firstly, and this goes back to the entire point of the previous module, always validate untrusted data. In the first example where I had the malicious search term, that is clearly not a legitimate thing to be searching for. So being explicit about what you want to allow on each input, and that means every point where untrusted data enters the system, that's critical. So having a whitelist of allowable or trusted data is an absolute must. Same again when it comes from an external service. So in that Whois example just before with the Harlem Shake, clearly when they were pulling Whois records, they weren't validating that the records were not malicious. The other really big thing about XSS, and this is really the core of defending against XSS, is encoding for the right context. The heart of the problem with XSS attacks is that untrusted data can execute on the page and change the behavior of that page. In the case where we ran the search, what we really should have been seeing is that entire XSS string appearing in the text that says you searched for and appearing in the search box itself. That is, of course, if it actually passes the validation I referred to in the previous point. But we should have seen it on the screen. We shouldn't have seen it rendered into the source code. Now it's important to get encoding right too, because we just saw two different contexts. So that is, it existed in an H2 heading tag, and we also saw it in the JavaScript context, so it was reflected inside a script tag. I talk extensively about context in my Hack Yourself First course, so that is absolutely critical if you're actually involved in building systems that need XSS protection. Another problem that made the attacks we saw before worse was the fact that sensitive cookies could be accessed by JavaScript. Now cookies have a paradigm called HTTP only, and when they're flagged as HTTP only, they can't be accessed by client script. They can still be sent back to the server and read by code that executes within the web framework, but they can't be accessed like we just saw with JavaScript. I show that in quite a bit of detail in the Ethical Hacking Session Hijacking course, and this again is another really fundamental security control. And finally, treat everything as suspicious. Trust no one. The who is example in the video before was a perfect example of this. They probably thought it was quite reasonable to assume that DNS records wouldn't have cross-site scripting attack payloads. But the assumption was the problem. And the assumption they really needed was the assumption that everything is out to get you. Because when you work from that position and you treat everything as suspicious, you're far better prepared for the times when it actually does turn out to be malicious. Now that we've covered both some attacks and some defenses, there's just one more thing I want to look at with XSS, and that's some ways of finding it and then ways of evading some of the defenses that I've just spoken about. To finish up on XSS, I want to share a couple of resources that are quite useful. And the first one is this one, xssposed.org, and it's a good collection of vulnerabilities and demonstrations of just how XSS works. And you can get a sense of what I mean by that when you look at the latest submissions. So for example, if we take a look at, say, clubs.london.edu, and there's a full disclosure statement here, so precisely where the vulnerability exists. And if we scroll down a little bit, we can see the vulnerable URL, and it looks like there's a reflected cross-site scripting attack in the query string, and down a little bit further, a screenshot of what actually happens when that cross-site scripting attack executes. Now this is just a proof. This alone is not a malicious attack, but it is the sort of thing that someone could then go and weaponize. And I'm showing it here just to demonstrate how broadly socialized these sorts of risks become. And it is actually an interesting resource in order to look at how these attacks are put together and what sort of patterns tend to be vulnerable in websites. So particularly as an ethical hacker, looking for ways to exploit the system that you're working on, resources like this can give you a lot of really interesting ideas. Let me show you one other one that's quite useful as well. This is OWASP's XSS filter evasion cheat sheet. And it's a really interesting resource that talks about some of the patterns that you can use to mount an XSS attack that circumvent filters that developers build into websites. So for example, earlier on I spoke about always validating untrusted data. Now what developers will often do to try and defend against the risk of XSS is look for, say, a script tag, and they'll expect that that is always the pattern that an XSS attack adheres to. But using filter evasion techniques, you can construct the XSS attack in ways that circumvents those defenses. If we scroll down a little bit, you can see some good examples. So for example, using the image source attribute to execute JavaScript, or perhaps changing the case of the characters used in the attack, just in case the filter is looking for a specifically cased attack. Malforming HTML tags is another good example. It's not semantically correct HTML, but the browsers will very frequently still execute it. And again, it can be used to bypass the patterns that filters are looking for. Or here's another one, setting an invalid image source and then setting an onError event on the image, such that when the browser fails to load that image, it executes the JavaScript in onError. So as you can see, there are lots of really interesting attacks, and this page goes on and on with a really extensive set of evasion techniques. So if you're working as an ethical hacker, trying to find cross-site scripting vulnerabilities in an application, go and check this out because it's enormously useful. So that's the end of XSS. Let's now move on and have a look at another aspect of client security, and that's validation. Earlier on, we looked at a persistent XSS attack. So that was one where we actually had cross-site scripting stored in the database, and then everyone who saw that record got hit with the XSS attack. Now I want to try and recreate that attack, and in doing so we're going to see another defense that's implemented on the client, which we're then going to circumvent. So here's what I want to do. I'm on the registration page. I'm going to enter an email address of jameshunt@f1.com. I'm going to give a first name of James, but this time for the last name, I'm going to paste in an XSS attack. And this is precisely the persistent XSS attack we saw just a little bit earlier. So that's going to be the last name. Now let me go on and set a password and confirm the password and try and register. And it hasn't really worked. We can see that we have an invalid last name. So there's something about this input that it doesn't like. And clearly it is malicious input, so it may well be that the application is just smart enough to recognize that and block the registration altogether. But one of the things I'm a little bit curious about is, was it the server that rejected this registration, or was it the client? So did the browser actually decline to even submit this to the server in the first place? Here's how we can find out. Let's hit F12 to open up the developer tools. I'm going to go over to the network tab. I'm going to then scroll back down to our register button, and let's now hit that again. Now there's been no network request, so this hasn't gone to the server. It looks like it's been rejected on the client. We can see why if we right click on this field and go down to inspect element. And in fact what we'll see here is that there's a data validation regular expression, and that regular expression only allows lowercase and uppercase alphabetical characters. Now that's what's blocking this script tag. It would also block anyone with a last name like O'Reilly as well, so this form actually has other problems. But what we're really interested in is the security side of things. So here's what I want to do to try and circumvent this control. I'm going to close the developer tools, and I'm going to go and bring Fiddler across again. So now Fiddler is running and capturing requests. Let's do this. I'm going to jump back over to the browser, and I'm going to change that last name to Hunt. So this should now pass the validation. Let's now go down and register. I'm going to flick back over to Fiddler. We can see some requests appearing, and now I'm going to stop capturing so that no other requests from my host appear here in Fiddler. Now the reason I've done this is to capture this first request, so the post request to register. And now that I have that, what I want to do is go and grab that request and drag it into the composer. The reason why I wanted to do that is because now I can modify that request body and add my malicious script and then see if we can register by posting direct to the server, thus circumventing the client-side controls. So here's what I'm going to do. I can't register twice with the same email address. So I'm going to go down and change it to jameshunt2@f1.com. The %40 is just encoding for the @ symbol. I'm then going to go and grab that last name, and I'm going to replace Hunt with my XSS payload. So this is the persistent one that we want to get into the database. Let's now go and execute this and we'll see what happens. So it appears to have run because we've got the same response again. We've got the 302, which then redirects to the home page at the root of the site and returns an HTTP 200. So we should now be registered with jameshunt2@f1.com. Let's now jump back to the website, and I'm going to log out the first James. So this is the James that we registered with the last name Hunt. So let's log that guy out, and then we'll go and log on with the new James. So this will be the James Hunt 2. Here's the email, here's the password, and now log on. So there we go. I've logged on with the account that has the XSS payload in the last name. The trick now is that I want to get that XSS payload displayed to other people. And the way I'm going to do that is I'm going to go and view the GTR, and I'm going to vote on it. And I'm going to now say, gotcha. Now, so far, that may seem pretty benign, but let me show you the significance. I'm going to go and log out James. And now I'm going to log myself back in. So this is my legitimate account. So I've successfully logged in. Now I'm going to go and look at the GTR. Let's see what happens. And suddenly I'm redirected. Here's that same evilcyberhacker.com website, and my cookies have been sent off. Now the reason why this happened is because when someone votes on a vehicle, their first name and their last name is recorded next to the comment. So what actually happened, and you might have seen it flash by very quickly, is that the GTR did load, and James Hunt's comment also loaded. But when his comment was shown, his first name and his last name with the XSS attack appeared in the source of the page. That's grabbed our cookies and it's redirected us here. So here's the point of what we've just seen. Client-side validation is great. It's very responsive, it saves callbacks to the server, it's a nice user experience. But the client can be easily circumvented. So you've got to complement every single client control with an equivalent server control. As an ethical hacker, when you're looking for vulnerabilities in a system, you want to look at every single control on the client that looks like it's designed to keep malicious content out of the system, and see if that control also exists on the server. So you just manufacture the request, just like we just saw. It could be in Fiddler or it could be in any other tool that allows you to construct an HTTP request and send it direct to the server. The other thing about this attack is HTTPS would not have stopped it. Transport layer security would simply load the XSS attack securely from the website. The victim would still have their cookies stolen, and there'd be no additional security simply by virtue of securing the transport layer. But of course, securing the transport layer is actually really important. Let's move on and start looking at insufficient transport layer security. What I want to talk about now is insufficient transport layer security. And I've laboured that point because this is really the key. Not just do you or do you not have TLS or SSL or HTTPS, and we do tend to use those terms a little bit interchangeably, but is it good? So a good example of this is the guidance here from PCI. And here they're making it clear that they've actually removed SSL as an example of strong cryptography. Now, when we talk about SSL, we are talking about the precursor to TLS. So SSL's time had well and truly passed once we hit the poodle bug of 2014. And even though it was considered a sufficient security control in the past, after that incident and as TLS succeeded it, SSL has now become insufficient. In fact, as of June 30, 2016, if you want to be PCI compliant, you simply cannot use SSL. But there's more to it than just that as well. Here's another statement by PCI. This is not just about using TLS instead of SSL. It is about using the very latest version of TLS instead of SSL. In fact, this version is so recent that there are still browsers in circulation that simply won't support it. But if you want to be PCI compliant, so if you're processing credit cards, you've got to run TLS 1.2. You can't run TLS 1.2 and 1.1 and 1.0. You must run only 1.2, and the other ones must actually be disabled. So that's an interesting evolution of transport layer security. And I wanted to begin this clip by showing that because it demonstrates how things change over time. And that's really important to the point about insufficient transport layer security. Before I do show you a demo of insufficient transport layer security, I want to quickly touch on the OWASP definition. And in fact, they define this as sensitive data exposure. And this actually covers a few different areas. It covers data at rest as well as data in transit. The thing that really stands out in their categorization of it, though, is the impact. Because by its very nature, sensitive data is important information. And exposing it, whether it is at rest or whether it's in transit, is very often going to have a serious impact. So that's just a quick look at how OWASP categorizes this. Let's now move on and actually mount an attack against insufficient use of transport layer security. There are many different examples of insufficient transport layer security, but I want to show you one that gives you a good indication of where things can go wrong. We're looking at the login form at the moment, and we'll see that it is not loaded over HTTPS. Now, I often see this conversation play out. Someone will say, hey, your login isn't secure. I can't see HTTPS in the address bar. And the organization will say, aha, but what you're missing is that if you look at the form, and I'll show you this one here because it demonstrates the behavior, we'll inspect the element, scroll up a little bit, we can see that the form posts to HTTPS. And what you often find organizations saying is that because it posts to HTTPS, then it's secure because the credentials are encrypted when the form posts. Now they're half right. It does actually encrypt the credentials when the form posts. But the thing that people miss with HTTPS is that it's not just about encryption. It's also about integrity. And the problem is that when you load a resource over HTTP, you can't have any confidence that it hasn't been modified. Now, how would that impact login security? Well, let me give you an example. Because this form loaded over HTTP, I mounted my own man-in-the-middle attack. So at the proxy level, I modified this page. And I'd like to show you what I did. If I go up here and expand the head, you'll see the last couple of lines here refer to evilcyberhacker.com. And what I've actually done is I've put a JavaScript keylogger on the page. So I've pulled in this external JavaScript file, and then I've set a destination variable, which is where key presses on the form should be sent when someone tries to log in. Now let me also briefly show you how I did this so that you can go and reproduce it yourself. I'm going to flick back over to Fiddler. And what you're looking at here, taking up most of the screen on the right, is Fiddler's script. Now remember that Fiddler is an HTTP proxy, and when your browser proxies traffic through it, Fiddler effectively behaves like any other point along the network where a man in the middle could intercept the traffic. So think of Fiddler as having the same power as the owner of the free cafe Wi-Fi, or the ISP, or the government with access to the internet backbone. The point is that it's sitting there on the wire watching the traffic. Now what I've done is used Fiddler script to modify that traffic. So we're looking here at the onBefore response event, which allows us to modify the traffic after the server has responded, but before that response has actually reached the browser. So it's upstream of the browser. Now this happens to be running on my PC, but again, this is exactly what a man in the middle can do at any point along the network. What I've done here is added in Fiddler script that looks for the hostname hackyourselffirst.troyhunt.com. It decodes the response to remove any compression or chunking, and it then gets a UTF string from those response bytes. Now I then build up this keylogger, and here we can see the two script blocks which I just showed you in the browser. What I then do is I replace the close head tag in that HTML response with the keylogger and then the close head tag. So I'm effectively appending the keylogger at the end of the head of the HTML document. I then set that into the response body, and that is that. The response that goes to the browser now has the keylogger injected into it. So let's see it all in action. I'm going to go back to the browser, and what that means is that if we now go and we have a look at the network tab, and I go up to email and start typing, every single key press is being sent off to evilcyberhacker.com. Most people think of a keylogger as being something which infects the client machine. But the concept of logging keys is something that can be done with JavaScript injected into the page. And indeed there are industry precedents of this as well. In fact, we've seen attacks by the Tunisian government against their people who were loading Facebook login pages in SQLi. Now, Facebook has long since fixed that risk, but there are plenty of other sites out there that haven't. So the thing you want to keep in mind with transport layer security is not just encryption of that sensitive information, but the integrity of anything that could have a security impact if the attacker could actually modify it. That is just one example of many different possibilities for transport layer security. And clearly the answer is to load everything of a sensitive nature over a secure connection. It's that simple. Let's now move on and have a look at one more attack that involves the client. The last risk I'd like to look at in this module is cross-site request forgery, otherwise known as CSRF. You may sometimes also see it referred to as XSRF. It's the same thing, just different acronyms. Now, OWASP also refers to CSRF in their top 10. It's getting towards the end, it's down there at number 8, but it is still serious enough to make the cut. Now, a bunch of these risk ratings are pretty much middle of the range. Average exploitability, common prevalence, and moderate impact. It is, however, very easy to detect, and as I said earlier, easy detection means it's easy for attackers to find. And as we'll see here in the description, CSRF simply takes advantage of the fact that most web apps allow attackers to predict all the details of a particular action. And really what we're saying here is that if an attacker knows what a request pattern should look like, and I'll give you an example of that in just a moment, they can trick the user's browser into making that request on their behalf. Now, in case that sounds a little bit odd, let's go and do a demo, and I'll show you exactly how that works. So back on our vulnerable site, and you'll see from the navigation bar, I am logged in. And CSRF attacks normally take advantage of the fact that the victim is authenticated, because what the attack is going to try and get them to do is perform an action that only they can do. Let me show you what I mean. I've just received a link from someone. I'm going to paste it up here into the address bar. Now, hypothetically, I've been sent this link and told that if I go there, I will win some stuff. Now, normally the domain is a little bit more innocent looking than evilcyberhacker.com, but the point is that a CSRF attack begins with nothing more than the victim loading a resource on the attacker's website. They may not even explicitly be going to it by following a link. It could actually be loaded as part of another page they visit. So for example, the attacker's CSRF page could be loaded in a hidden iframe on another site. Let's see what happens though. I'm going to load this page. And this all looks innocuous enough. The check is in the mail. I must have won stuff. Something is going to come to me. But something else happened when we went to this page, and I want to show you what it is. I'm going to hit F12 to open the developer tools, and we're already on the network tab. Now here's what I want to do. Let me go and reload this page, and we'll take a look at the requests that are made. So here we go, a bunch of them are just popped up down the bottom. I'm going to scroll all the way to the top, and I'm particularly interested in the first two. So the top one is the page that we just requested here. So /win stuff on evilcyberhacker.com. Number 2 is the really interesting one, because the domain that you see there is hackyourselffirst.troyhunt.com. It is a post request and it's going to change password. Let's drill down on that request and see what's actually happening. So here we can see the full path, /account /change password. There's the request method, it's a post. And if we scroll all the way to the bottom here, we see our form data. And the form data is sending two fields, new password and confirm password. And they're both set to hacker, with an @ instead of an A and a 3 instead of an E. Now this is the form data that is required to set a new password. And what this attack has done is effectively replicated what a legitimate change password request looks like. Now the reason why this has worked is evident if we scroll up just a little bit. And what you'll see here is our auth cookie. So remember, the auth cookie is the thing that keeps us authenticated as we make requests across the site. I talk about the auth cookie extensively in the Ethical Hacking Session Hijacking course, because stealing auth cookies is what that course is all about. The problem is that the browser automatically sends this cookie simply because it is valid for the domain of the request. That's how cookies work. The upside for the attacker is that they can exploit that implementation by tricking the browser into making a request. Which begs the question, how did this page trick my browser into making the request? Let's have a look. I'm going to press Ctrl-U to view source, and here's what the page looks like. Now this is actually really simple. There's a form here, and the action of that form is that change password path. Now it's going to post, we can see the method there, and when it posts, it's going to target hidden frame, which is further down on line 12. And hidden frame is just an iframe that has no display. So it's functional, but you won't actually see it in the browser. The really important part of this page, though, is the two hidden input fields on line 9 and 10. And these are simply input fields that replicate the legitimate fields on the change password page. And that page requires a new password and a confirm password. Doesn't matter that they're hidden forms, they still get sent in the HTTP request exactly the same way. The final piece that ties all of this together can be seen on line 6 on the body tag. And it simply says that when the body loads, submit the form. So what ends up happening is someone merely goes to this page, and as soon as that page loads in the browser, the form is automatically submitted. Now, if that person is logged on and has a valid auth token cookie, this attack works. Their password is now hacker. So what that means is that the attacker now knows the user's password, and they could then go on there and do whatever they like with the account, including then changing the password to something else altogether. The reason this works is because the form we see here simply replicates a legitimate form. The request that occurs when this page loads is identical to the request from the change password page. Predictability is the problem here, and the solution is randomness. Now, randomness, in terms of protecting against CSRF, is achieved by using an anti-forgery token. And I talk about anti-forgery tokens extensively in my Hack Yourself First course. So if you want to understand more about the defense of a CSRF attack, go and check out that course and you'll see exactly how it works. So that's CSRF. It's an enormously powerful attack that takes advantage of the client. That's the last attack involving the client that I want to look at. Let's now move on and summarize the module. Let's summarize the module. And one of the things that I hope is now pretty clear is that it can be very difficult for the client to know when it's being attacked. Reflected cross-site scripting, for example. There are some defenses that you can use against that sort of attack. And in fact, in the first module, we looked at some native defenses within the browser. But there are lots of conditions that can't be picked up by pattern alone. So it's very hard for the browser to know what actually constitutes a real attack. It's especially hard for the browser to know when that cross-site scripting is persistent. So it can't look at the input that goes into the request, and then draw conclusions about the malice of it based on the response to the request. So it is a tricky thing to solve at the client level. The other thing that's tricky is input validation, and you need to do it. It should be there. But as we saw from some of those XSS evasion techniques on the OWASP cheat sheet, there are a lot of different ways of delivering an XSS payload. So a defense like this, which again is important, is rarely comprehensive enough to block every attack. Now, of course, in your capacity as an ethical hacker, that then means there's lots of different options available if you find the right combination of characters to probe the system with. And I really strongly recommend using that OWASP cheat sheet in order to find some of those weaknesses. The thing with all these attacks though, is that there are appropriate controls. So controls like output encoding to prevent XSS, enormously effective if it's done properly. TLS, good TLS, puts a man-in-the-middle risk at bay. And indeed, as I mentioned earlier on, good TLS is becoming increasingly mandated by the likes of PCI. And finally, the bit we just looked at was CSRF and anti-forgery tokens. Get those tokens right, and that is the end of CSRF. And again, a course like Hack Yourself First goes into a lot of detail, including demonstrations of just how those anti-forgery tokens work. And they're critical for protecting against CSRF. So that's a bunch of different attacks involving the client. Lots of different ways to exploit a system based on where weaknesses might exist. Let's now move on and look at attacks against identity management and access controls. I want to start with just a couple of examples of weaknesses in identity management. And these are rather glaring weaknesses, but they're good illustrations of just how badly we can get identity management wrong. So take this one for example. Just take a moment to read what this login process is. Now, of course, keeping in mind that a mobile number is public. It's something you give people. Indeed, that's how you receive phone calls. So this is a really good, blatantly bad example of a login implementation. It really doesn't get much worse than this. But let me show you another example of bad identity management. This one was covered quite extensively in the press earlier in 2015. Part of that may be because I did write about it after the organisation involved didn't seem to see a problem with the implementation. But if you take a moment to read through it, what you realise is that the password reset feature only needed a username, which by default is the email address, and a birth date. Now, after you provided those two pieces of information, you could reset the password. No verification via email. You didn't have to demonstrate that you actually owned the email address. All you had to do was show that you knew the birth date of the person who owned the email address. The irony of this particular case was that the organisation said, hey, your username is sensitive data. You shouldn't be sharing it. But it's your email address. That's how you get email. You share it with other people. And as for birth date, that is obviously a personal attribute which is shared extensively, not just with your friends, but via other channels such as social media. It's not hard at all to discover someone's birthday. So these two pieces of information together were enough to reset an account, which then gave you access to money. In this case, money in a gambling account. So these two examples do set a bit of a low bar in terms of just how bad identity management can be. But I wanted to start here just to give you a little bit of a sense of the level that we often have to deal with these challenges on. And certainly, if you are wearing the ethical hat and you're looking for vulnerabilities in systems, implementations like this do tend to stand out somewhat. So hopefully that sets the scene for how bad it can be. Let's now start to look at some specific implementations of identity management that have weaknesses in them. And I want to start with identity enumeration. Let's go and have a look at that now. I want to start with just a couple of examples of weaknesses in identity management. And these are rather glaring weaknesses, but they're good illustrations of just how badly we can get identity management wrong. So take this one for example. Just take a moment to read what this login process is. Now, of course, keeping in mind that a mobile number is public. It's something you give people. Indeed, that's how you receive phone calls. So this is a really good, blatantly bad example of a login implementation. It really doesn't get much worse than this. But let me show you another example of bad identity management. This one was covered quite extensively in the press earlier in 2015. Part of that may be because I did write about it after the organisation involved didn't seem to see a problem with the implementation. But if you take a moment to read through it, what you realise is that the password reset feature only needed a username, which by default is the email address, and a birth date. Now, after you provided those two pieces of information, you could reset the password. No verification via email. You didn't have to demonstrate that you actually owned the email address. All you had to do was show that you knew the birth date of the person who owned the email address. The irony of this particular case was that the organisation said, hey, your username is sensitive data. You shouldn't be sharing it. But it's your email address. That's how you get email. You share it with other people. And as for birth date, that is obviously a personal attribute which is shared extensively, not just with your friends, but via other channels such as social media. It's not hard at all to discover someone's birthday. So these two pieces of information together were enough to reset an account, which then gave you access to money. In this case, money in a gambling account. So these two examples do set a bit of a low bar in terms of just how bad identity management can be. But I wanted to start here just to give you a little bit of a sense of the level that we often have to deal with these challenges on. And certainly, if you are wearing the ethical hat and you're looking for vulnerabilities in systems, implementations like this do tend to stand out somewhat. So hopefully that sets the scene for how bad it can be. Let's now start to look at some specific implementations of identity management that have weaknesses in them. And I want to start with identity enumeration. Let's go and have a look at that now. I want to start with just a couple of examples of weaknesses in identity management. And these are rather glaring weaknesses, but they're good illustrations of just how badly we can get identity management wrong. So take this one for example. Just take a moment to read what this login process is. Now, of course, keeping in mind that a mobile number is public. It's something you give people. Indeed, that's how you receive phone calls. So this is a really good, blatantly bad example of a login implementation. It really doesn't get much worse than this. But let me show you another example of bad identity management. This one was covered quite extensively in the press earlier in 2015. Part of that may be because I did write about it after the organisation involved didn't seem to see a problem with the implementation. But if you take a moment to read through it, what you realise is that the password reset feature only needed a username, which by default is the email address, and a birth date. Now, after you provided those two pieces of information, you could reset the password. No verification via email. You didn't have to demonstrate that you actually owned the email address. All you had to do was show that you knew the birth date of the person who owned the email address. The irony of this particular case was that the organisation said, hey, your username is sensitive data. You shouldn't be sharing it. But it's your email address. That's how you get email. You share it with other people. And as for birth date, that is obviously a personal attribute which is shared extensively, not just with your friends, but via other channels such as social media. It's not hard at all to discover someone's birthday. So these two pieces of information together were enough to reset an account, which then gave you access to money. In this case, money in a gambling account. So these two examples do set a bit of a low bar in terms of just how bad identity management can be. But I wanted to start here just to give you a little bit of a sense of the level that we often have to deal with these challenges on. And certainly, if you are wearing the ethical hat and you're looking for vulnerabilities in systems, implementations like this do tend to stand out somewhat. So hopefully that sets the scene for how bad it can be. Let's now start to look at some specific implementations of identity management that have weaknesses in them. And I want to start with identity enumeration. Let's go and have a look at that now. I want to start with just a couple of examples of weaknesses in identity management. And these are rather glaring weaknesses, but they're good illustrations of just how badly we can get identity management wrong. So take this one for example. Just take a moment to read what this login process is. Now, of course, keeping in mind that a mobile number is public. It's something you give people. Indeed, that's how you receive phone calls. So this is a really good, blatantly bad example of a login implementation. It really doesn't get much worse than this. But let me show you another example of bad identity management. This one was covered quite extensively in the press earlier in 2015. Part of that may be because I did write about it after the organisation involved didn't seem to see a problem with the implementation. But if you take a moment to read through it, what you realise is that the password reset feature only needed a username, which by default is the email address, and a birth date. Now, after you provided those two pieces of information, you could reset the password. No verification via email. You didn't have to demonstrate that you actually owned the email address. All you had to do was show that you knew the birth date of the person who owned the email address. The irony of this particular case was that the organisation said, hey, your username is sensitive data. You shouldn't be sharing it. But it's your email address. That's how you get email. You share it with other people. And as for birth date, that is obviously a personal attribute which is shared extensively, not just with your friends, but via other channels such as social media. It's not hard at all to discover someone's birthday. So these two pieces of information together were enough to reset an account, which then gave you access to money. In this case, money in a gambling account. So these two examples do set a bit of a low bar in terms of just how bad identity management can be. But I wanted to start here just to give you a little bit of a sense of the level that we often have to deal with these challenges on. And certainly, if you are wearing the ethical hat and you're looking for vulnerabilities in systems, implementations like this do tend to stand out somewhat. So hopefully that sets the scene for how bad it can be. Let's now start to look at some specific implementations of identity management that have weaknesses in them. And I want to start with identity enumeration. Let's go and have a look at that now. Here we are back on the sample vulnerable web application, and we can currently see the login page. Now I want to give you an example of identity enumeration, and this risk becomes really clear once it's demonstrated. What we want to do in this scenario is establish whether someone has an account on the site. So rather than logging in, what I'm going to do is go over to the Forgot Your Password link. Now to demonstrate the enumeration risk, I'm going to start by entering an invalid email address. So I'll just enter foo@bar.com. Let's try and reset that. And here we have a very clear message. The specified user does not exist. Let's try something different. Let's try my account because I know that I do have an account on this website. So I'm going to enter my email address, and now let's try and reset. This time, your password has been reset and you should receive an email with a new one shortly. So see how we get a different response. One advises us that the account doesn't exist. The other one advises us that the account does exist. So this actually becomes a privacy risk. This website is leaking the identity of members if you specifically ask it if an email address exists. Now for a website like this, that may not matter too much. And what I mean by that is that in a privacy sense, would a member of this website be too upset if others could discover that they were voting on supercars? Probably not. But let me give you another real-world example. In 2015, we saw the hack of Ashley Madison. 37 million accounts were exposed, and there was outrage that this website had disclosed who had an account on the site. But I wrote a piece in July 2015 where I showed that the website would disclose that anyway because the password reset had an enumeration risk. Now, Ashley Madison was a website designed to encourage people to have affairs. Confidentiality is enormously important on a site like that, and the ability for anyone to go and check if anybody else had an email address on that site and consequently draw the conclusion that that person was out to have an extramarital affair is an enormous violation of privacy. So that's an example of where enumeration would be a serious problem. What I'd like to do now, though, is show you a really good implementation that defends against this risk. Let's go over to the EntroPay website. This is EntroPay, and they allow you to have virtual credit cards. So clearly, it is a financial site, and security is going to be paramount to these guys. Now, here's what I'd like to show you. Let's go and repeat the same process as we just did on the sample vulnerable site. I'm going to go down to Forgot Password. And I'm going to go and enter a fake email address. So let me go up to here, and the one I'm going to use is testenumeration@mailinator.com. Now I'll show you why I've chosen that specific email address in just a moment. Let's now go and submit this and see what happens. Okay, here we go. Email sent. We have sent you an email at testenumeration.mailinator.com with further instructions. Now remember, we've just manufactured this email address. It almost certainly doesn't exist as a valid account. The trick here is that if it was a valid account, you'd get exactly the same message here on the screen. Where things diverge, though, is that you'd get a different email. Now, the reason I used mailinator.com as the domain of this email address is because we can now go and check what's in the email box of the test enumeration account. Let me jump over to Mailinator now. Okay, so let's now type in test enumeration and we'll check that email box. And here we can see just a couple of minutes ago we got an email from EntroPay support. Let's go and take a look at what's in that email. And here's an interesting message. You or someone else entered this email address when trying to change the password of an EntroPay account. However, this email address is not on our database of registered users. Now this is great because email ends up being the channel by which the account is either confirmed or denied, not the anonymous attempt to reset the password. And that's really the heart of defending against the enumeration risk. You always have to give the same response whether the account exists or not. Now that doesn't just go for the password reset. It's the same thing with registration as well, because registration facilities often confirm whether an email address is already in the system. You might have seen this before. It says, hey, you've already registered with that email address. You can't register again. And the solution to that is the same. You have to give the same response on the website and then confirm via email whether that account exists or not. That's something I go into more detail on in the Secure Account Management Fundamentals course. Now there's just one more thing I'd like to show you about account enumeration. Let's go and take a look at a graph. This is a graph of login timings. And it shows a really interesting trend. Every single time I tried to log into this particular website I was testing with an account that didn't exist, it responded very, very quickly. So those red bars show that the response came consistently at about 130 milliseconds. Now, every time I attempted to log in with an account that did exist, that timing was always over 500 milliseconds. Now, regardless of whether the account existed or not, you got the same response from the web app. It said, hey, this combination of username and password is not correct. But the timing gave it away. So by observing the behavior of the web app and literally timing how long it took for the response to come back, I could easily conclude whether the account existed or not. The reason this happened is because the web application was using a very slow hashing algorithm. Now, this was actually good news. Web applications should use slow hashing algorithms for their passwords. And we'll talk about that more towards the end of this course. But the risk you then end up with is disclosing the presence of the account, because the hashing was only happening if the account existed. So when you logged on, the web app would attempt to go to the database and pull back the record for the username that was provided. If that record existed, then it would hash the password that was provided and compare it to the one that was stored in the database. If the record didn't exist, it would never hash the password that was provided. Now, that's an efficient technology design, but it leads to an enumeration risk because all you have to do is look at the timing of it. So that's all I want to cover here for identity enumeration. But it does speak to those nuances that I mentioned at the start of this module. There are lots of little aspects of identity management you have to get right in order not to have risks like this. Now, conversely, as an ethical hacker, there are lots of different aspects of an identity management implementation that you can probe away at and almost certainly find risks. Here we are back on the sample vulnerable web application, and we can currently see the login page. Now, I want to give you an example of identity enumeration, and this risk becomes really clear once it's demonstrated. What we want to do in this scenario is establish whether someone has an account on the site. So rather than logging in, what I'm going to do is go over to the Forgot Your Password link. Now, to demonstrate the enumeration risk, I'm going to start by entering an invalid email address. So I'll just enter foo@bar.com. Let's try and reset that. And here we have a very clear message. The specified user does not exist. Let's try something different. Let's try my account because I know that I do have an account on this website. So I'm going to enter my email address, and now let's try and reset. This time, your password has been reset and you should receive an email with a new one shortly. So see how we get a different response. One advises us that the account doesn't exist. The other one advises us that the account does exist. So this actually becomes a privacy risk. This website is leaking the identity of members if you specifically ask it if an email address exists. Now, for a website like this, that may not matter too much. And what I mean by that is that in a privacy sense, would a member of this website be too upset if others could discover that they were voting on supercars? Probably not. But let me give you another real-world example. In 2015, we saw the hack of Ashley Madison. 37 million accounts were exposed. And there was outrage that this website had disclosed who had an account on the site. But I wrote a piece in July 2015 where I showed that the website would disclose that anyway because the password reset had an enumeration risk. Now, Ashley Madison was a website designed to encourage people to have affairs. Confidentiality is enormously important on a site like that. And the ability for anyone to go and check if anybody else had an email address on that site and consequently draw the conclusion that that person was out to have an extramarital affair is an enormous violation of privacy. So that's an example of where enumeration would be a serious problem. What I'd like to do now, though, is show you a really good implementation that defends against this risk. Let's go over to the EntroPay website. This is EntroPay, and they allow you to have virtual credit cards. So clearly, it is a financial site, and security is going to be paramount to these guys. Now, here's what I'd like to show you. Let's go and repeat the same process as we just did on the sample vulnerable site. I'm going to go down to Forgot Password, and I'm going to go and enter a fake email address. So let me go up to here, and the one I'm going to use is testenumeration@mailinator.com. Now I'll show you why I've chosen that specific email address in just a moment. Let's now go and submit this and see what happens. Okay, here we go. Email sent. We have sent you an email at testenumeration.mailinator.com with further instructions. Now remember, we've just manufactured this email address. It almost certainly doesn't exist as a valid account. The trick here is that if it was a valid account, you'd get exactly the same message here on the screen. Where things diverge though, is that you'd get a different email. Now the reason I used mailinator.com as the domain of this email address is because we can now go and check what's in the email box of the test enumeration account. Let me jump over to Mailinator now. Okay, so let's now type in test enumeration and we'll check that email box. And here we can see just a couple of minutes ago we got an email from Entropay Support. Let's go and take a look at what's in that email. And here's an interesting message. You or someone else entered this email address when trying to change the password of an Entropay account. However, this email address is not on our database of registered users. Now this is great because email ends up being the channel by which the account is either confirmed or denied, not the anonymous attempt to reset the password. And that's really the heart of defending against the enumeration risk. You always have to give the same response whether the account exists or not. Now that doesn't just go for the password reset. It's the same thing with registration as well, because registration facilities often confirm whether an email address is already in the system. You might have seen this before. It says, hey, you've already registered with that email address. You can't register again. And the solution to that is the same. You have to give the same response on the website and then confirm via email whether that account exists or not. That's something I go into more detail on in the Secure Account Management Fundamentals course. Now there's just one more thing I'd like to show you about account enumeration. Let's go and take a look at a graph. This is a graph of login timings, and it shows a really interesting trend. Every single time I tried to log into this particular website I was testing with an account that didn't exist, it responded very, very quickly. So those red bars show that the response came consistently at about 130 milliseconds. Now, every time I attempted to log in with an account that did exist, that timing was always over 500 milliseconds. Now, regardless of whether the account existed or not, you got the same response from the web app. It said, hey, this combination of username and password is not correct. But the timing gave it away. So by observing the behavior of the web app and literally timing how long it took for the response to come back, I could easily conclude whether the account existed or not. The reason this happened is because the web application was using a very slow hashing algorithm. Now this was actually good news. Web applications should use slow hashing algorithms for their passwords. And we'll talk about that more towards the end of this course. But the risk you then end up with is disclosing the presence of the account, because the hashing was only happening if the account existed. So when you logged on, the web app would attempt to go to the database and pull back the record for the username that was provided. If that record existed, then it would hash the password that was provided and compare it to the one that was stored in the database. If the record didn't exist, it would never hash the password that was provided. Now that's an efficient technology design, but it leads to an enumeration risk because all you have to do is look at the timing of it. So that's all I want to cover here for identity enumeration. But it does speak to those nuances that I mentioned at the start of this module. There are lots of little aspects of identity management you have to get right in order not to have risks like this. Now conversely, as an ethical hacker, there are lots of different aspects of an identity management implementation that you can probe away at and almost certainly find risks. Another feature of identity management that I've often seen done very poorly is the Remember Me feature. This is the little checkbox you see on the screen here, and it'll be very familiar to you. You see it on many different sites on the web, and it allows the user to return to the website in an authenticated state without having to log in again. There are web applications where this makes a lot of sense. Facebook, for example. You want people to keep coming back to the site with a very, very low barrier to entry. So already being authenticated and immediately seeing your social feed is quite a valuable feature for Facebook. However, the way this feature gets implemented can be very weak, and I'd like to show you that now. So here's what I'm going to do. I'm going to log in with my normal email address and password, and I'm going to check the Remember Me box. Let's now log in. Okay, that login went just fine. Now I'd like to show you precisely how this Remember Me feature has been implemented. So what I'm going to do is hit F12 to bring up the developer tools. I'm going to head over to the Resources tab, down to Cookies, and then take a look at the cookies for this site. Now there are two cookies here I want to point out. One is there's a cookie called Email, and there's my email address. Now you'll notice that it has an expiry in September 2016. That's 1 year from now. So this cookie is going to last a long time. The other cookie worth noting is the password cookie. And if we have a look at the value, it doesn't look like your typical password. And indeed, I have used a really poor password. It's not what you see here. But this does look like a familiar pattern. Let's take a closer look at it. I'm going to copy it, and then I'm going to jump over to base64decode.org. Let's now drop that cookie value into here, and we will decode it. Now just beneath that decode button, we can see the decoded base64 string, and it is password with a 0. That is the extremely poor password that I use on my account on this vulnerable web app. The Remember Me implementation on that site simply looks for that email cookie and the password cookie when you come back to the site, and it actually repeats the login process. So base64 decodes the password value, posts it to the login URL along with the email address, and you are logged in. That is how it does Remember Me. I've seen multiple examples of this. In fact, I've got a blog post on how to implement a secure Remember Me feature that also demonstrates some pretty bad ones. Sometimes without even base64 encoding the password, it just puts it in a cookie. Not that base64 encoding gives any protection, but it just demonstrates that they didn't even try to obfuscate the password. Now let's jump back to the website for a moment, because there's one other thing I want to show you. Have a look at the HTTP column. So this is the indicator of whether the cookie is HTTP only or not. And neither the email or the password are. So think back to the XSS attack from the attacks against the client module. And back there, I managed to access all the non-HTTP only cookies by a very simple reflected XSS attack. I also showed how to do it with a persistent XSS attack. Those XSS attacks that sent all the cookies off to the attacker would have direct access to both the email cookie and the password cookie. That's now credential theft, so that becomes a very serious issue just because of the way this data is stored. And the thing you need to remember with credential theft, and we'll talk more about this later on in the course as well when we look at password storage, is that credential theft is about more than just a risk to the website that disclosed the credentials, but it's also a risk to everywhere else that the user of the website reused their password. It's a terrible practice, but it happens extensively. So the impact of disclosing a password, even on a site where it may not be protecting anything of too much significance, can be severe. So that's the last thing I wanted to cover on attacks against identity management. Let's start looking at access controls, and specifically resources that are missing them. I want to start with a basic definition, and this definition is going to carry us through the remainder of the module. And it looks like this. This is really the crux of it, making a network resource unavailable. Now there are many different ways to make that network resource unavailable, and that's really the point of this module. We're going to go through and look at a number of different exploits that can be used by attackers to make sure that the victims can't access the web application that's being targeted. To begin with though, I'd like to quickly touch on a couple of different types of denial of service attack. These are a couple of very broad categories: targeted at an individual and targeted at an entire service. Now let me explain these two more clearly. So firstly, when we're talking about targeting at an individual, we're talking about attempting to disrupt just a single user. Now inevitably, for an attack of this type, it is very specifically targeted. There is something about this individual that's causing the attacker to single them out. So for example, perhaps the victim of an attack is an opponent in a gaming system, and the attacker wants to knock them offline so that they can't compete against them. Or another scenario could be that the victim is bidding in an auction, and the attacker is also bidding, and they want to remove the competition by denying the victim's service and making the auction site unavailable specifically to them. Now, what tends to happen on these very individually targeted attacks is there's an exploit in something such as a password reset or a login feature. And I'm going to talk more about both of those as we proceed through the module. You may also find a distributed denial of service or DDoS attack against an individual. I mentioned gaming just before, and we've actually seen this attack quite frequently where an adversary mounts a distributed denial of service attack against the target's IP address, so floods their network with malicious traffic such that they can't play the game. That may sound a little bit insignificant, but inevitably some people take their gaming very seriously. Now moving on to the attacks that target an entire service. Really what we're talking about here is trying to take the whole thing offline. And these are often the attacks that we do see hitting the news headlines, because it can result in the web application being taken offline for everyone. This is not about trying to knock one person offline or deny access to a service just for one person. It's often about causing maximum impact, making everything unavailable to everyone. Now, for that style of attack, we do frequently see it as a distributed denial of service attack. And I'm going to talk about a couple of different ways that DDoS attacks can be mounted. One of those ways that we'll look at more closely a little bit later on is using a dedicated DDoS service to take the web application offline. And yes, such a thing does exist. DDoS as a service. I'm going to give you a couple of examples of that later on in this module. For now though, let's move on and take a look at a specific example of locking one individual out of a web application and denying them service. I want to do a quick demo of how poorly designed password reset feature can be used to deny service to a victim. We're on the login page, but I am going to jump over to the forgot your password page. And up here, I'm going to enter my email address. Now keep in mind that anybody can go to a password reset page and enter anybody's email address. This is not an authenticated action, and indeed the whole premise of being here is that you can't authenticate. You've forgotten your password. Let's have a look though at what happens when I begin the reset process. Your password has now been reset. So that's it. It's changed. I can no longer log on with the old one. Now, yes, I will get a new password in the mail, but as it stands right now, until that email comes, there's nothing I can do. I can't get into the system. Not only that, but until I check my email, I've got no idea that somebody else has already changed my password for me. Now, you do sometimes see this. It's not that uncommon, and it's a real flaw in the implementation because it allows you to lock someone else out. Now, yes, I could go to my email, get the new password and log back in. But what if the attacker kept hitting this? So what if the attacker continued to reset my password? In fact, with no anti-automation such as a captcha, this would be very easy to automate. They just keep sending an HTTP request to this resource and sending my email in the request body. Keep that on a loop and I'm permanently locked out of my account. So how should this feature work? Well, it's very simple. Let me show you. That's it. Never lock it out immediately. You've always got to send an email with a reset link. Now, it has to be a sufficiently random reset link, and there are nuances around things like having a time-limited nonce in that link. I talk about that in detail in the Secure Account Management Fundamentals course, but this is really the crux of avoiding the denial of service attack. If you don't lock the account out, an attacker can't keep the legitimate owner of the account out. And that's really, really important if you don't want to have one of these individually targeted denial of service risks in your application. So that's one way of denying service on an individual level. Let's go and take a look at another way. Conventional wisdom says that multiple simultaneous attempts to log into a web application that fail should result in a message somewhat like this. Often the guidance is to simply lock the account out. You've tried to log in too many times, make the account unavailable. But think about this in the context of a denial of service attack. If I know someone's username, all I've got to do is send 5 incorrect passwords, just make them up, and submit those to that login page, and the user's locked out. They can now no longer log back in. I have denied them service. And as I just mentioned with exploiting the password reset, you could always automate this too. So as an attacker, you could keep sending invalid credentials to the login resource. And then even if the account gets unlocked, they just get locked out again. So whilst you don't want to have completely unbridled access to keep trying to brute force an account, you've also got to be conscious of the fact that it can be used to deny that user service. Now, of course, this then begs the question, how should you handle multiple failed attempts to log in? Let's have a look at some ways. To be clear, the risk that we're talking about here is brute force. So an attacker is trying all sorts of different passwords against the one account to try and see if they can guess the right one. Now, sometimes that may be manual. The attacker may be using a very rudimentary attack where they're just trying to guess what the person's password is. Or it could be highly automated, so the attacker could write a script which goes through a common set of passwords and attempts to find the one that matches the account. In both cases, though, there are less invasive ways of defending against the risk. So one is to slow the rate of login attempts. So as there are consecutive failed attempts, the rate at which the attacker can attempt new passwords on decreases. That doesn't lock the legitimate user out for any long period of time, but it does enormously decrease the effectiveness of the attacker. Another option is to allow them to unlock the account via email. And for all intents and purposes, this becomes logging in via email. So that is, an email is sent to the account owner and they're then invited to click a link, provide their credentials, and log in. That verifies that only the legitimate owner of that email address can use the link to log in. And it also keeps an external attacker away from continually trying username and password pairs. You still have the risk that the legitimate owner could go to the website and not be able to log in, but at least now there's a side channel, that is sending an email, which helps them get around that problem. There are also ways of verifying identity via other independent channels. So for example, SMS or phone. Hey, you've tried to log in too many times and failed. We've just sent you an SMS with a one-time password that you can use to log back in. Of course, that then requires other processes in place, not least of which is that you've got to know the person's number, and you really need to verify it as well. Certainly, if you're going to implement any sort of lockout, you are going to need a mechanism for unlocking. One thing you do want to be a bit cautious of is trying to lock out via other attributes. So for example, trying to lock out via IP address. A good example of where that doesn't work is in 2014, GitHub got hit with an enormous denial of service attack. And what they found was 40,000 unique IP addresses attempting to log on not to the one account, but to a whole variety of different accounts, and at a slow rate, so they weren't just sitting there hammering the one account, they were rotating through them all. So in that case, just trying to lock out an IP address wouldn't really work, because the nature of the distributed attack via the botnet meant there were all these unique IP addresses. That's a pretty high-end example, and certainly there's a case to be made by using other attributes of the request to either throttle the speed of logins or block it entirely for a period of time. But hopefully it demonstrates how this is actually not an easy problem to solve. It's another nuanced problem. There are lots of different edge cases, and you need to find the right balance for the particular system that you're working with. So that's account lockouts, and that's the last I want to cover on those individually targeted denial of service attacks. Now let's go and look at larger scale attacks. Let's look at distributed denial of service attacks. DDoS attacks, or distributed denial of service attacks, have become enormously prevalent in recent years. Just before recording this, I thought I'd go and grab some headlines just to show the sort of thing that's going on at the moment. And the headlines that you see appearing on the screen now have all been from just the last few weeks. I wasn't even aware of many of these. They simply weren't significant enough in my news feed to even stand out. I'm sure that many of these weren't even on the front page. I'm sure that many of these never even got much airtime. DDoS attacks are now so common that they're often not even reported on. Now, of course, the really large ones, or the ones that do have serious impact on the target, will make the headlines. But there are a huge number of DDoS attacks that are either small in nature, have very low impact, so they might be very short-lived, or they impact a lower value target that simply isn't even newsworthy. But before we go on, let's just take a quick look at precisely what a DDoS attack is. When we talk about a distributed denial of service attack, we're talking about many different attackers all targeting the one service. So conceptually, it looks a little bit like this. Now, these guys might be spread out all over the world, and we'll look at some ways that can happen in just a moment. But they're all targeting the one system, and DDoS attacks very frequently tend to be volumetric. So that is, all of these attackers are trying to send sufficient malicious traffic to the target website such that it can't service legitimate requests. So to pick a physical world example, imagine you have too many people trying to fit through a doorway at the one time. They can't. They get jammed. If it's just a normal rate of people, that's fine. They go through without any problem. But when you try and squeeze way too many through at the same time, you end up with service being denied. The legitimate people that want to use the doorway can't get through because there's too many other people trying to get through at the same time. And in very simplistic terms, that tends to be what happens in a DDoS attack. Get enough people trying to jam packets through to a web server at the same time, and it's going to struggle to handle the legitimate ones. These attacks also often tend to be globally distributed. They come from all over the world, and that's one of the things that can actually make them extremely difficult to defend against. If those attacks originate from foreign countries, tracking down the perpetrators and indeed stopping the attacks can be extremely difficult. I'd like to show you a fantastic visualization of what a DDoS attack looks like. And in fact, what I want to show you is what DDoS attacks that are occurring right now look like. Let's go and take a look. The Norse map of real-time DDoS attacks is mesmerizing. This is what is happening now. This is where we are seeing attacks originating from and being directed to. And as you can see, they're going all over the world. Look at some of the origins in the table in the bottom left, and indeed some of the attack targets as well. Certainly you do see a pattern with particular countries, which in itself is quite interesting. We also see different attack types, so attacks that exploit different protocols, different ports, and bombard those with huge amounts of data, which again make it very difficult for the target system to actually serve legitimate requests. One of the other things that should stand out on this map is just how many different locations there are sending these attacks. And certainly if you go and take a look at the URL in the address bar now, you'll probably see quite a different pattern. Different attacks originating from different locations and targeting different services. This shows you just how prevalent these DDoS attacks have become. But of course it then begs the question, how do you launch a DDoS attack? Let me show you a couple of different ways. One common way of mounting DDoS attacks that became particularly prevalent with the hacktivist movement is crowdsourcing them. Now what I mean by that is that you'd see tweets like these. And then some instructions on where to fire your lasers at. These tend to be calls to arms for hacktivists to join together and target a particular web application in what amounts to a distributed denial of service attack. So in this case, you've got a collection of individuals, inevitably spread out across the world, all targeting the one web application. Now, if you get enough of these individuals making enough requests, then it's possible to take that targeted website offline. Now, there are a lot of variables in terms of what is enough traffic to take it offline, and we'll talk about those a little bit more later on. But certainly if messages like this can coerce enough people, possibly thousands of people, to simultaneously bombard a website with malicious traffic, then it could indeed take it offline. We've seen attacks like this be successful against the likes of PayPal in the past, so certainly they do have a track record of causing outages. Now another thing that you may notice in many of these tweets here are the letters LOIC, or LOIC, and LOIC is a favourite of hacktivists. I want to show you what LOIC looks like and how it works, so let's go and take a look at that now. This is the Low Orbit Ion Cannon, otherwise known as LOIC. So this is the tool that we kept seeing featured in those tweets earlier on. And again, it's a favourite of hacktivists because it's freely available software. They run up on their machine and simply target a website. You get enough people running LOIC together and targeting the same website, and it may be taken down as part of a distributed denial of service attack. Now LOIC is an extremely basic tool. We simply enter a URL, so let's pick our sample vulnerable website, and then lock on. Now when we lock on, it resolves the domain to an IP address. There are a few other options that can be defined here as well in terms of how the attack packets are formed and then the destination they're sent to. For example, the port, which will default to port 80 because that's what HTTP runs over by default. We'll choose a method, TCP, UDP, or HTTP. We'll go with HTTP for the moment. And then other attributes such as how many threads to run and then what speed you'd like the process to run at. I'm going to leave everything else where it is at the moment. And this exercise is not so much to teach you how to mount a DDoS attack using LOIC, because as an individual you can't mount a DDoS attack. You need other people as well, otherwise it is not distributed. And the fact that it is not distributed is really not going to make it a denial of service attack either, because one individual just using LOIC is not going to be enough to take any website offline. But that said, let's hit I'm a charging my laser and start LOIC targeting our website. Now as we can see in the attack status down the bottom, it's simply going through making connections and issuing requests. That's all that's happening. Now depending on the nature of the website, TCP or UDP packets may be a more impactful denial of service attack. And certainly some of the operations we've seen hacktivists running have provided explicit instructions on tailoring LOIC to launch an attack in a customized way so that it does result in maximum carnage. The main thing to take away from this though is just how easy it is to run this software. So you can see how hacktivists, who are frequently kids, get involved in these DOS attacks, because this is all it takes. Fire up Loik, put in a URL, and start the attack. If you're the one orchestrating these attacks, so long as you can get enough people to run Loik and repeat this process, you may well actually be able to take the target website offline. And again, there is a history of this style of attack actually being quite effective. But it is also very rudimentary. It's a simple tool and it requires crowdsourcing. DDoS has moved beyond that. In fact, DDoS is now frequently available as a service. Let's go and take a look at what I mean. DDoS as a service. Many different services like the one you see here have appeared in recent years, and the concept is not complex. All they need is enough machines targeting the one web application, and they may well be able to knock it offline. Now, they could obtain those machines through a botnet, so that would be a collection of infected, legitimate PCs that are now under the control of a botmaster, or in some cases they'll even use cloud-based services in order to distribute out enough clients to generate traffic that takes that target down. Now, you'll also see two other terms used on the website here, stressor and booter. And both of these are really the same thing. They're distributed denial of service as a service. They may be promoted as stress testing tools, but these are not designed for performance testing your own applications in any sort of a legitimate way. There are very good legitimate services that actually do that, and they do that ethically. But these services are expressly designed to take other people's systems offline. They're easily available for anyone who can create an account and pay for the service, and often it will use a cryptocurrency or other means of payment that are difficult to trace, and they can be enormously effective. Certainly they can be very cheap, which is part of the reason why they have become so prevalent. Now, an example like this may also look pretty basic as well, not exactly professional, and certainly that is often the case. But we're also seeing DDoS evolve. We're seeing it turn into a more professionally managed service. Let me give you an example of that. That is a rather polished video, and clearly that is promoting a professional DDoS service. Now, this particular one has been taken offline, but in its place many others have emerged, and increasingly they are run like professional businesses, because there can be big business in running a service that allows you to take other web assets offline. Competitors' web apps, for example. And we've seen documented cases where that has been effectively corporate espionage. Now, one of the things with any sort of denial of service attack is how the attack is actually targeted. Let's go and take a look at some specific features of web applications that are at greater risk of a DDoS attack. Earlier on, when I demonstrated Loik, I simply pointed it at the root of our sample vulnerable website, and Loik went away and made a heap of HTTP requests. Now, certainly if you get enough instances of Loik making enough requests, then yes, it could take the service down. But a more effective way of launching a DDoS attack is to target specific features of a web application. So, for example, anything that causes the password to be hashed. In the last module, I showed a graph of login timing, which showed just how slow it is to log on when a good password hashing algorithm exists. And that workload, hashing the password, puts enormous strain on the infrastructure if it's hit enough times. So if you were launching a DDoS attack, you'd be looking to target a feature of the app that causes high overhead, such as anything that hashes the password. So login hashes it, registration hashes it, changing the password hashes it. Any one of these three facilities that so many websites have would be a natural choice for a DDoS target. Another one would be a feature that connects to another service. So for example, a page that connects to SMTP. A password reset, for example, usually sends an email. If that's connecting direct through an SMTP server, there can be hundreds of milliseconds of latency on that. If you can launch a DDoS attack and have hundreds of different threads tied up trying to reset the password, that could well stop the application from serving legitimate requests. Another one again would be a resource that hits the database. And the reason for this is that often web applications will have a pool of available connections. And a connection pool DDoS would be where that pool is exhausted. So many requests come in from the DDoS attack that all the connections are used servicing those requests and are unable to service legitimate requests. So again, it's a similar principle. Keep the website busy dealing with the malicious traffic such that it can't serve the legitimate traffic. Also consider other high-load functions. So for example, perhaps running a report needs to execute an expensive database query. You may not even need that many simultaneous connections. If the database is working hard enough and an attacker is asking it to do it many times over in parallel, that could prevent legitimate queries from being run. Same again if there's a large data set returned. So what if there's a search, for example, that returns a large number of results and it's hit over and over again, not consecutively but simultaneously? Is it going to be able to handle all those requests? And of course, from the attacker's perspective, that would give their attack much more leverage than if they just hit a very fast resource with very low overhead on the server. So these are just a few different ways that an attacker can accelerate the effectiveness of a DDoS attack. And it also should be a reminder for those defending systems to be really cautious about the resources that have a high overhead on them as well. So consider if they may pose a high risk to the threat of a DDoS attack. I'm going to talk about improper error handling, but I want to touch on this OWASP top 10 definition to begin with, and clearly it is security misconfiguration. Now this is a fairly broad topic, it encompasses many different things, but one of those things is the leaking of internal error messages. So what we're going to see in this clip is how an internal error message can be leaked, and then when combined with another risk, how it can be exploited to expose sensitive information. Now by OWASP's definition here, the exploitability of security misconfiguration is easy, and you're going to see just how easy it is in a moment. They've also classed detectability as easy, and you've probably seen many times before where you've been on a web application, clicked a button, and then suddenly seen an internal exception due to the fact that the application has implemented improper error handling. So in terms of how easy it is to detect, you can just stumble across it by accident when using an application exactly as it was intended to be used. So let's move on and take a look at just how damaging it can be when errors are improperly handled. So it's back to our sample vulnerable web application again. And I'm going to scroll down a little bit, and then I'm going to click on View NISNs. Now we've got one NISN here, we've got the GTR, and that's fine. But what I'm really interested in is the URL. Now this URL appears to have a combination of a very semantic-based routing convention, where we can see that we're looking at make number 1, and it has a query string as well. As we learned very early on in the course, both of these components of the URL are untrusted data. Now that means we can modify them as an attacker and potentially get the application to do unusual things. Here's what I want to do. I want to go and change the make from number 1 to number 100. Let's see what that does. And here we see an internal exception. And this exception has bubbled up, or in other words, it has appeared in the browser rather than just being encapsulated on the server. Now the exception we're seeing here is sequence contains no elements. So this alone is actually giving us a little bit of information about what's going on in the underlying system. And if we were to speculate, we'd say that make 100 doesn't exist. And somewhere in the code, it's taking that piece of untrusted data, going to the database, not getting a result, and then the code is unable to handle the fact that the sequence doesn't contain an element for make 100. Now in this particular exception here, we've also got a stack trace. So this is detailed internal implementation data about exactly what is going on. This allows us to start building a picture of how this application is behaving internally. Further to that, if we scroll down to the end of the page, we'll see that we've got framework version information. So there's the .NET framework version, and there is the ASP.NET version. So that's pretty detailed information. That would be enough to reproduce the sort of exercise we did earlier on in the course with Drupal, where we identified a vulnerable Drupal version, went to Shodan, searched for it, and then located every site that might be at risk of that really serious SQL injection flaw. So this is another little piece of information leakage which can be valuable to an attacker. But I want to take this a step further. We know that this page is improperly handling exceptions, and it would also be fair to speculate that a page like this is probably hitting an underlying database. So in this case, there is probably a table of makes, and when we hit this page and we hit it with make 100, it's probably going to the database and attempting to get a record. Now I'd like to use a very small SQL injection attack here. Let me paste the SQL injection attack into the URL. Now take a quick look at what's happening here. It's the same path, albeit with make number 1, which we know successfully loaded, and the order by query string has now got a SQL statement after it. Select top 1 password times 1 from user profile. Now again, there's an entire course dedicated to SQL injection in the Ethical Hackers series, so I'm not going to explain everything that's going on here again. What I will say though, is that this query is going to execute in the database, and it's going to try and multiply the first password in the user profile by 1. Let's see what happens when this runs in conjunction with improper error handling on this page. We get an error message which is now enormously useful. Conversion failed when converting the nvarchar value password with a 0 to data type int. This is an internal password from the user profile table in the database, and we are now seeing it in the user interface. So what we've just done is exploited the fact that this application has implemented improper error handling, and we've then caused an internal exception in the database. So the message that I just read out is an actual error message from the database itself, which has then been returned to the web application and then bubbled up into the user interface. So this is how these attacks chain together. Improper error handling in conjunction with the SQL injection risk means that we can get passwords out of the database. Now this is just one very, very small part of SQL injection. And again, I do encourage you to go and watch that course in order to better understand it. But it's a perfect illustration of just how devastating improper error handling can be. Let's now move on and look at something quite different, and that's insecure cryptographic storage. Insecure cryptographic storage is actually a pretty broad topic because there are so many different ways that we can implement cryptographic storage of sensitive data. Now, OWASP does cover this in their top 10 web application security risks, and in fact it was risk number 6, sensitive data exposure. And one of the things that they talk about in sensitive data exposure is improper use of cryptographic paradigms. And that's exactly what I want to show you here. So I'm going to show you one of the most common misconceptions about how passwords should be stored in systems. And that's how storing passwords as salted hashes is often done in a weak fashion. Now, in order to explain that, I need to begin by explaining what a salted hash is. So let's run through the process here. And I want to talk first of all about registration. Now let's imagine we have a user who wants to register in a system. Now, as part of the registration process, the user provides a plain text password. That's submitted to the server, along with other data in the registration process, of course, things like a username and other typical registration type data. That doesn't matter too much for this example. The point is, they register and provide a plain text password. Now, when we talk about a salted hash, what the application does is it generates a salt, which is a set of random bytes. It then takes both the salt and the password that the user has provided, and it hashes them. Now, both those attributes, the salt itself and the hash of the salt and the password, get stored in the database. Now, why do we do this? Well, here's the reason. If you have multiple users create the same password, because the salt is always unique, you'll always end up with the unique salted hash. The reason that's beneficial is because it makes the cracking process of those hashes enormously slower. So for example, if you had 100 users use the password, but with a 0 instead of an O, if you were just creating a direct hash of that password, every output would be the same. You'd crack it once and every user's password would be compromised. However, if you generate a salt, then 100 users with the same password means 100 different salted hashes. Now, not only does it mean that the salted hash is different for users of this system with the same password, but it also means that any other users of any other systems using the same password always have a different salted hash. That makes the pre-computing of hashes useless. So we used to see a lot of rainbow tables, which were basically just large tables of pre-computed hashes. So someone would go through and pre-compute all of, say, the MD5 algorithm hashes for the top 100,000 passwords. And then you'd compare that to the passwords breached from a system that were also stored with MD5, and whenever there was a match of the hash, the rainbow table would also provide a map to the plain text equivalent. So this is why we salt. Now let's talk through the login process as well, just to make it clear how this works later on when the user comes back to the system. So we'll start with our user again. The user logs in by providing the username and the plain text password. So this is what we all do when we log into a system. It's just those two attributes. That goes to the web application. Now the web application takes the username and sends it off to the database. And effectively what it's doing is just saying, hey, get me the user who owns this username. The password isn't involved yet, it's just checking by username. Now the database responds, and if it finds a user for that username, it brings back the salt and the salted hash of the password. So this is what we just saved earlier on in the registration process. If the database doesn't find the username, it can just simply say, hey, your login credentials were incorrect. But assuming it does find that username, it comes back with the salt and the salted hash of the password. Now the web application can then hash the plain text password that was provided by the user with their salt that was just retrieved from the database and compare it to the salted hash that was stored in the database. Now if they match, the web app can respond and say, hey, now you're logged in. If they don't match, the web app can respond and say that the credentials were incorrect. So this is how the cycle works. It always depends on recreating the stored hash by looking at the plain text password the user provides and the salt that is stored for them in the database. Now people believed this was a good mechanism, and parts of it are good, but parts of it are also very weak. And the weakness comes because of the fact that if the database gets leaked and the salts and the salted hashes are exposed, then you can effectively go through and recreate this logon process using cracking software. When we talk about cracking password hashes, we're not talking about breaking the algorithm. We're simply talking about reproducing this process. So that's what we're going to do now. And I want to begin by showing you what a collection of salted hashes stored in the database actually looks like. So these are salted SHA-1 hashes. And in fact, what we're seeing here is each row having two fields separated by a tab. The first field is the salt. So remember, this is the randomly generated bytes that are created for each unique user. The second field is a SHA-1 hash of the password and salt. So this is the one that's always going to be unique, even if the same password is used, because that value on the left is a randomly generated salt. Now both of these are base 64 encoded, and in fact what we're looking at here is salts and salted SHA-1 hashes created by Microsoft's ASP.NET membership provider that was present in Visual Studio 2010 and earlier. For many years, this was the default standard for storing passwords. And certainly it wasn't just for Microsoft. This was a generally accepted industry practice. And salted SHA-1 hashes remain one of the most common ways of storing salted hashes today. But this is weak. It's enormously weak. And I want to show you the problem. Let me now minimize this window, and behind here, we're looking at a command prompt. And the command that I've got sitting here ready to go is one that's going to run hashcat. Now hashcat is free hash cracking software. It's enormously good hash cracking software. And what it's going to do is crack our salted SHA-1 hashes. The way it's going to do it is it's going to take that file of hashes I just showed you, and it's also going to take a password dictionary. And that's the parameter you can see here, hashkiller.com.dic. And a password dictionary is just a collection of strings that are common passwords. So not necessarily actual words that you'd find in a typical language dictionary, rather passwords that are commonly used across various systems. So I now want to run this, and we're going to see how quickly it manages to crack our salted hashes. And that's it. It's done. So now that it's executed, I want to take a moment to talk through what's actually happened. First of all, what we saw scrolling through the screen was each row of our salted hash. And we can see part of the salt and the salted hash still left here on the screen. It's got some other data around it which formats it in a way that Hashcat can understand. Now off to the right, we're seeing the plain text version of that particular salted hash. So for example, Ninja, password with a 1. All of these were in the password dictionary, and Hashcat then took them, added the salts to them, hashed them, compared them to the stored salted hash, found a match, and then came back and reported that yes, indeed, this is the plain text password. Now it's the stats down the bottom that make this particularly interesting. So first of all, this only took 4 seconds to run. This was rather fast. During that 4 seconds, the GPU, so my graphical processing unit, so that's the graphics card of my PC, which is enormously efficient at calculating hashes, it managed to create 18,241.1 kilohashes per second. So in other words, it was creating 18 million hashes every second. Now because of that, it managed to recover 29 out of 30 of those stored salted hashes. So this was just a pretty short list. Often you'll find systems contain thousands or even millions of stored hashed passwords. So clearly this was an enormously effective exercise. And many people are very surprised that you can compute 18 million hashes per second. But they're even more surprised when you see just how fast you can compute hashes if you approach things a little bit differently. Let me show you the Hashcat website for a moment. Hashcat has some really interesting stats here on just how fast it can run. And in the performance section, you'll note that they talk about 4 different PCs. The top couple of rows show a couple of different GPU architectures, one being an AMD HD 7970 and the other being an NVIDIA GTX 580. These are consumer-level graphics cards. They're high-end graphics cards, but we're still only talking about hundreds of dollars for something that people run to, say, play games, so fairly commonly found GPUs. Now if we scroll down a little bit, we'll see just how fast these GPUs can run for different types of hashing algorithm. So let's take that first machine, the one with the 7970. If we were using MD5 hashes, it could calculate 8.5 billion of them per second. Now that figure is so much higher than what we just saw, because rather than feeding the hashes in via a password dictionary, this example has the source passwords generated entirely in the GPU. So for example, it will simply say, give me a range of 6 to 8 lowercase characters. You don't then become I/O bound by having to feed in passwords. It can all happen internally. Now MD5 is also a much faster hashing algorithm than what we just saw with SHA-1 as well. But even SHA-1 is still over 3 billion hashes a second. So this is enormously fast. And incidentally, that 7970 launched back in 2011 as well. So things have gotten significantly faster since then. So that's all I want to cover on the hash cracking itself. Let's now look at how to do this properly. And I've got a great resource to share with you. This is the OWASP Password Storage Cheat Sheet, and it's a fantastic resource for helping you decide how to properly store passwords. Now I'll point out just one thing here, and it's this: work factor. The key thing with password hashes is that they need to be slow. So they need to be slow enough that it makes the cracking process infeasible. As the hash process gets slower, the success rate of the attacker declines dramatically. So for example, if we could make the hashing process 1,000 times slower than what we just saw, instead of 4 seconds, it's going to be 4,000 seconds, and that's only for the 29 hashes we cracked as well. Make it 10,000 times slower, and now you're starting to look at seriously detrimenting the ability to crack those hashes. A really important point here is that this protection is not about absolute security. It's not about making them uncrackable. It's about making it so infeasible that only the weakest passwords are going to be cracked, and the vast majority of them, assuming users are using good passwords, which is a different challenge altogether, are going to remain safely secured. So that's just one example of insecure cryptographic storage. Let's now move on and look at something totally different, and that's unvalidated redirects and forwards. Unvalidated redirects and forwards is another one in the OWASP top 10. It does come in last place, so it is the least risky of those top 10 risks, but it still makes an appearance, and it has done for several versions now. The main thing that stands out here in their risk rating is detectability. It's very easy to find when there is a risk of an unvalidated redirect and forward. And in fact, this is a pattern that you'll see in many different applications. Part of what makes this one a little bit contentious is that there are some valid use cases for having an unvalidated redirect and forward. Let me show you a legitimate use of it, and then we'll go and exploit it. Let me demonstrate how a redirect or forward should function under normal operating circumstances. We're on our insecure site. I'm currently logged off. I've got a log in link on the navigation bar. Now imagine I tried to go to an authenticated resource. So for example, let's say I tried to go to this URL. So have a look at it. It's this nice semantic pattern again. I'm trying to go to account, user profile, number 1. This is the resource where you edit your account. But I'm not logged in. So watch what happens as I try to load this page. I'm taken to the login page, but have a look at the URL. It's got a query string called return URL. And in that return URL, there's a URL encoded value, so the forward slashes are being converted to %2fs, that refers to the original URL that I tried to load. So watch what happens now when I log in. Email address, password, login. You see how I'm now on that edit profile page? So what's actually happened is after posting my credentials, to the login page, including that redirect URL query string, it's authenticated me and then returned me to the page I was originally trying to access. That's neat. It's a nice little usability feature. But let's now exploit that. So I'm going to go and log off from my account. And now I'm going to go up to the address bar and I'm going to paste in a URL that someone has given me. This is pretty long, so let me jump back to the start. And now you can see the entire URL. Now there is something here in the return URL, but it's an obfuscated value. In fact, it's URL coding of every single character in the query string. Now here's the thing in terms of this being an attack vector. I, as the victim, have received this URL. When I look at it, I see a domain that I trust. I know this website, hackyourselffirst.troyhunt.com. Now imagine that's your bank, or a government website, or another address that you have confidence in. If someone gives you that, you're going to have a higher degree of confidence in the integrity of what comes after you load that link. But let's do that. Let's now actually follow that link. Okay, so it wants me to log in. Now we are actually on the legitimate site. We can still see hackyourselffirst.troyhunt.com in the address bar, so it must be okay. Let's now enter my email address, password, and log in. Now as soon as I do this, we can see a file has downloaded. It's a file called malware.exe. And what you may have actually noticed is that the status bar very briefly showed evilcyberhacker.com. So that's our malicious website again. Now here's how this happened. Take a look at the URL in the address bar now, and particularly that return URL. Google Chrome has automatically translated most of the characters from their URL encoded values back to the original value. And now we can actually get a sense of what's happening. It's gone to evilcyberhacker.com/malware.exe. So what we have done as an attacker is use the redirect of the login page in order to send the victim to a URL serving malware. So we're looking at a malicious file that has been downloaded, but we're looking at a trusted domain in the address bar. And this is really the crux of an unvalidated redirect and forward. It's exploiting the trust that individuals have in the domain of a website in order to serve them malicious content. Now in this case, Chrome has obviously highlighted that this is not a commonly downloaded type of file and could be dangerous, which is great for Chrome. Not all browsers are quite as obvious, and of course not all attacks on an unvalidated redirect and forward are quite so blatant. They're usually not called malware.exe. It might instead take the victim to a phishing page or another potentially malicious resource. So that's an unvalidated redirect and forward in action. Now the defense against this is usually pretty straightforward. In a case like this, it should only be able to redirect to local resources. You should not be able to redirect to an external website. There are other use cases where you need to redirect to other external websites, in which case it's better to create a whitelist of allowable websites. You can then still use this URL pattern, but only if the return URL in this case is a trusted site. However, there are also use cases where that redirect may need to be any arbitrary external site. You'll often see patterns like that with, say, social media sites or online email providers, where they want to redirect you through one of their resources when you follow an arbitrary link that's been sent to you by someone else. In those cases, an unvalidated redirect and forward isn't even a bug. It's actually a feature. So you've got to be a little bit conscious about how valid this actually is as a security risk, but certainly this is how it can be exploited. Let's now move on and have a look at a totally different sort of risk, and that's exposed exception logs. Let's now look at quite a different class of risk to what we've seen already, and that's when internal logs are unintentionally exposed publicly. Now it's very easy to discover that this is an ASP.NET web application, and I know that one of the most common logging frameworks that are used for ASP.NET web applications is Elmar, and I also know that Elmar is frequently accessible via this path. And here we have Elmar. This is the exception logging modules and handlers for ASP.NET. It's a third-party component, but it's enormously popular. It's meant to be secured, so it's only accessible via authorized users, but as you can see here, that is unfortunately not the case. I am not presently logged in. So this has actually been served up to me as an anonymous user. And in fact, you can go to this address right now and see exactly what we're seeing here, assuming that there have actually been some exceptions to log. Now we're seeing the exceptions from earlier on in this module when I showed you improper error handling. And in fact, we've got 2 exceptions here. Let's go and take a look at what we can see in these. I can drill down into the details, and here we have that internal stack trace from before. So this again is what I showed you on improper error handling. Elmar logs all this because it's enormously useful to system administrators who want to debug exceptions. But of course it's also enormously useful for attackers, because here's all of that stack trace information we saw earlier on. It's worse than that though, because as we scroll down, we'll also see all the server variables. And the server variables include the HTTP request, and the HTTP request has got the auth cookie in it. Now, as I show in my ethical hacking session hijacking course, once you have the auth cookie, you have the user's identity. This exception occurred while I was authenticated as troyhunt@hotmail.com. What that now means is that if an attacker comes to this page, copies that auth cookie value and recreates it in their own browser, they will become me. Now attackers know about these common log file patterns. They know that Elmar is a commonly used ASP.NET framework, and they know about other common frameworks for other common languages. So as an ethical hacker, this is exactly the sort of thing that you want to be looking for, because it provides enormously useful information. Now I also want to give a sense of just how prevalent exposed logs are on live production websites. So I want to run a quick Google Dork, or in other words, a very carefully crafted Google search that's going to expose all sorts of results that you wouldn't expect to normally find on the web. So let me go and drop this search into the address bar. In URL, elmar.axd, because Elmar does frequently appear with the .axd handler, I'm going to make sure that the file type is actually AXD, so it's not just a presence of elmar.axd in the URL string, it does actually refer to the file type AXD, and then error log 4, because that's the text that appears on the Elmar error log itself. Let's see how many results we find. 13,700 results of exposed Elmar logs. That is just amazing. All of these sites are exposing exactly what we just saw. Sensitive internal information that's easily accessible by anyone just by doing a simple Google search. I've obfuscated the URLs here because clearly this is a majorly sensitive piece of information. But equally clearly, it's extremely easy for anyone to go out and find the presence of these log files. So this is definitely the sort of thing that you want to be testing for in your web apps. And obviously make sure that you are looking for the common frameworks in the actual language that the app is built on. So that's exposed exception logs. Enormously easy to discover and an enormously serious risk. Let's go on and look at one more thing in this course, and that's vulnerabilities in web services. Let's wrap the course up by talking about one last thing, and that's vulnerabilities in web services. And I'd like to begin just by touching on a couple of slides from my Hack Your API First Pluralsight course. Now that course goes into extensive detail on the sorts of risks we find in APIs and all sorts of connected devices. And right up the beginning of that course, I talk about connected devices relying on connected services. As more and more connected devices have emerged, so everything from phones to modern PCs to tablets, we've seen more and more dependencies created on APIs. So this is services that still run on web servers, still talk over HTTP or HTTPS, but are invoked in the background. So they're not web applications loaded in a browser, rather it's a dedicated client talking to a service. Now often those clients are loaded from app stores, the Google Play Store, the Microsoft App Store, Apple's App Store, and a variety of other locations that serve up rich client apps to modern devices. There are literally millions of apps in these stores, and a huge proportion of them are talking over the web to web services. But it goes well beyond just personal computing devices that are talking to connected services. Increasingly, we're seeing connected things talk to web services. These scales, for example, I use these myself. They measure your weight and your body fat, and then they send it back to an API, so you can track how they change over time using a device like your smartphone. We're even seeing door locks that are now connected devices. So devices like Lockytron and many others that have followed since, which communicate to APIs and take instructions from them. This is a door lock, something that opens your house, dependent on a service served over the web. And of course, cars are becoming increasingly internet connected. There's an API ecosystem for Tesla. You can write your own apps and call APIs on their service, which can then communicate with your vehicle. So clearly, web services providing APIs to these sort of devices are not only becoming very common, but they're becoming very critical because they're controlling real-world things. So their security profiles are enormously important. And when we're talking about hacking web applications, it's absolutely essential that we're also hacking these APIs, because that's how we're going to make them stronger. But here's the thing with the way these services work. They're not that different to web applications. This is all still HTTP communication. Most of the risks that you've seen throughout this course apply equally to the web services as they do to the web applications. So have a think about some of the things we've looked at. Insecure transport layers, tampering of parameters, insecure cryptographic storage. All of this is equally relevant in web services. But of course, there are also some differences. Let's go and take a look at those. Whilst there are a huge number of similarities between web applications that load in the browser and services that sit behind rich clients, there are also some key differences. So for example, the services are normally returning XML or JSON instead of HTML. The services themselves don't return the markup. The rich clients take care of that presentation tier. The services are merely returning data. Many of the attacks that we'd launch against dedicated web applications that load in the browser are still the same, but some attacks that target the client, so for example cross-site scripting, do change quite significantly. The other thing that's quite different with this style of web application is authorization, and we normally see that persisted via something like a bearer token or an auth header instead of via a cookie, which is what we typically use in a web application. So that does have some impact on the style of attack we might launch. We also see that web services, and particularly web APIs as we're coming to know them, do increasingly make use of semantic HTTP verbs. So as I mentioned earlier on in the course, this is things like using the put verb and not just always the post, or using the delete verb if you want to delete a record, rather than say passing delete as an action in the query string. Now this of course does change the attack vectors a little bit. You're probably more likely to find that HTTP verb tampering will yield results in an API than what you'll find in a typical web application loaded in the browser. The nature of the way web services are built, and particularly when they're stood up behind rich client apps, does also mean there are some slightly different risks. So for example, visibility. When it's an API behind, say, a mobile app, they are somewhat less visible. So what I mean by that is that you're not seeing a URL in the address bar. One of the things I talk about extensively in the Hack Your API First course is that when you use a mobile app, you've got no idea if it's talking over a secure connection or not. You can't see a padlock in the address bar. You can't inspect the certificate. And for testers using the system, they can't see it either. It is very easily discoverable. You can simply proxy the device through Fiddler and have a look at the traffic. That's another thing I do extensively in that course. But without specifically probing at the security implementation of the app, you simply can't see that. The other thing is that when developers are building the client, as well as the server, it's very easy to get things like certificate validation wrong, or as I've often seen, even in banks, to not have any certificate validation at all. When you're building a web app that loads in the browser does this automatically. The developer cannot turn off the fact that the browser does that. That works great when the browser is the client, but when a developer is building the entire client themselves, which is effectively what they're doing with a rich client app installed on a mobile device or an Internet of Things thing, they can disable certificate validation. They can get that wrong themselves, and they frequently do. One more thing as well, and that's the fact that dangerous assumptions are often made when someone believes they control the whole ecosystem. So when a developer builds both the client and the server, I frequently see them making the assumption that the client will only ever talk to the server in the way they designed it to happen. So they often neglect things like the ability to tamper with parameters. We know how that works now, we've seen that throughout this course, but what the developer of the rich client app often misses is that just like we took the browser out of the picture and used wget and burp and fiddler and all these other tools to go straight to the server, you can easily take the client out of the picture when it's a rich client app talking to an API. There's a much greater risk of incorrect assumptions about integrity being made when the entire ecosystem is custom built. So that's both the services on the back end and the client itself. And I see that time and time again. But as I've said, have a look at that Hack Your API First course. And I've even got a custom mobile application in that course to show you exactly the sort of things that developers get wrong in terms of not understanding how attackers operate. So that's vulnerabilities in web services. Let's go and summarize the module. Let's summarize the module. And one of the first things we covered in other attacks on the server is all about how seemingly minor risks, so risks such as improper error handling, can actually be turned into full-blown exploits. So we saw that internal stack trace and the version information of ASP.NET when I originally tampered with the URL on the page showing the Nissan. That in itself was very minor, but when we combined that with a SQL injection attack, we started getting passwords out of the system. Now this is really important to remember because often people will say, hey, this bug, it's just one little thing. In and of itself, it really isn't dangerous. But you've always got to think about how can that be combined with other risks in order to become something altogether more serious. Another thing we saw in this module, and indeed something that's come up many times across the entire course, is how security is frequently about degrees and context. So for example, we just looked at insecure cryptographic storage, salted SHA-1. Many people would consider this secure, but clearly we also cracked it really quickly. Now over time, the view of the security of salted SHA-1 has changed quite dramatically, particularly as GPUs get faster and cracking gets more efficient. And this is why today we're looking at algorithms that have a much higher workload. But even then, we come back to degrees again. It's not about making sure that no passwords can be cracked. It's about minimizing the number of passwords that can be cracked and making other trade-offs in the process. And then context, unvalidated redirects and forwards. There are times when this is very useful. It can be a feature of the application, but it can also be used in malicious ways. Sometimes you can mitigate that. But of course, there are also cases where you need to be able to redirect to anywhere in an unvalidated fashion. So the context of how that feature is implemented and whether or not a security control is suitable is enormously important. And finally, modern applications talking to web services. And that's not just modern applications in phones and tablets and PCs, but it's modern applications in everyday household items, Internet of Things, even cars. And increasingly, these are talking to services over HTTP running on web servers, just like the web application we've been looking at throughout this course is built on. So this opens up an all-new frontier of potentially exploitable software. And that means for you, as an ethical hacker, your attack surface goes up enormously, not just because of this emerging class of software, but because of how quickly we're seeing new devices become dependent on internet-connected services. So that's other attacks on the server, and indeed that now wraps up the entire Ethical Hacking Web Applications course. Thank you for watching. I'm Troy Hunt.